Hello and welcome to Tech Simplified TV. Today we have a very special episode for you. It's a marathon episode based on one of the most important topics in VLSI design, clock and delay. In Tech Simplified TV, we have already published videos based on clock tree synthesis, clock network routing, and different other aspects of clock. In today's episode, we will combine them all for your convenience. So we will start with foundation of clock network design in VLSI. Next, we will move to clock tree synthesis. We will try to understand different important parameters like delay, jitter, slew, and latency. Next, we will explore the advanced routing technique. From there, we will dive into clock gating. Clock gating is one of the most important power-saving technique in VLSI design. We will try to understand different types of clock gating techniques. Then we will shift our attention to different types of delay in VLSI design. We will understand what are cell delay, path delay, transition delay, skew, jitter, latency, etc. After that, there are three segments from static timing analysis. We will try to understand STA engine, timing path. Next, we will move to STA delay and delay calculation. And finally, we will conclude our discussion with in-depth analysis on design constraints and their role in static timing analysis. This marathon is designed to give you a complete understanding into clock and delay. So if you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, clock tree and clock tree synthesis. Next, clock network. There are another slide on the very same topic, that is clock network. After that, challenges of clock network. Here also two slides on that topic. Then clock skew, jitter, latency and slew. Next, clock parameter and their impact. After that, conventional clock tree distribution. Next, clock mesh, H-tree and fishbone, multi-source clock tree system. And finally, there is another slide on multi-source clock tree system. So these are the pointers we will cover in today's episode. So now let's move to the first slide. Clock tree and clock tree synthesis. We already have an episode on clock tree synthesis. In our recent episode on power management series, we have discussed a little bit about clock tree synthesis, clock tree optimization, clock gating as a part of power management in an IC. Now here we will concentrate our discussion on clock tree and different aspect of it. This is a diagram of a clock tree. Both are diagram of clock trees. This one, the left one, represent before CTS and this one represent the scenario of clock tree after CTS, that is clock tree synthesis. So first, let's try to understand what a clock tree is. A clock tree is a clock distribution network within a system or circuit. Clock tree includes the clocking circuitry and device from clock source to destination. Clock tree is a very important and integrated part of a circuit or chip. So a sequential circuit works as a sequential because of clock. In a circuit or a design, clock signal must be present in each and every sequential leaf level component or flip-flop. Therefore, clock signal has to travel a longer path, and we already have discussed that in power management series. Clock signal travels a longer path and consume a lot of power. So that is very important from aspect of power management. Here we will discuss about clock tree, its structure, its parameter, its challenges, about all of these things. Complexity of a clock tree and its number of clocking components used depends on the circuit and in its functionality. A clock tree, how much complicated it should be, depends on the number of components present in the circuit, and number of components in the circuit, sequential component in the circuit, depends on the complexity of the function it is performing. If the function is really complicated, a lot of work a design is doing, then its circuitry is complex, and the clock tree and its components and its complexity is also higher in such cases. Now, systems can have multiple ICs with different clock requirement. In a system, there could be multiple ICs which has different clock requirement. A clock tree refers to the various clocks feeding to those ICs. Usually, a single reference clock is cascaded and synthesized into multiple different output clocks. This is the basic mechanism. First, a reference clock is usually there, a single reference clock, and multiple output clock is synthesized from there. We will see it later. Because this is the scenario before clock tree synthesis. Clock root, and this is a source, this is a destination. Clock root is the source and destination is a leaf level flip-flop. And before synthesis, it's directly connected. And after synthesis, that connection has been cascaded through some buffers. This level of buffers that gets included in CTS. This is the contribution of CTS. Now, clock tree synthesis is the process to distribute clock to each sequential element of the circuit. CTS is part of physical design in backend flow. This is the total flow, and here the backend portion CTS is done. RTL design is verified and synthesized into a technology mapped gate level netlist. RTL coding, verification. So it's starting from design specification, then RTL coding is done, then verification is done. On that, synthesis is done, and we get a technology mapped gate level netlist. Now after that, DFT is done, floor planning, and after that it's going in backend. So floor planning, power planning and routing, global placement, detailed flow placement, these are all done. Now comes clock tree synthesis. So CTS comes after all these steps. Till now, ideal clock is used. Since all sequential elements are placed, real clock signal are included in CTS. So without CTS, clock signal goes to each end leaf cells or flip-flops directly from clock root. After CTS, there are a number of buffers inserted so that proper power management could be done. So this is the importance of clock tree synthesis that is done on clock tree. Now we will try to understand what are the parameters, how a network works, what are the different parts of this clock network, and etc. So we are done with this slide. We will move to the next slide. Clock network. This is the first slide on clock network. Clock network consists of a clock generator, clock elements are there, and clock wires. The clock can be generated by using ring oscillator or other non-stable circuit, but these are susceptible to PVT variations. PVT we know, process, voltage, and temperature. These are the basic three reasons for variations. We have discussed about PVT variations. We have many episodes on PVT variations and variability. In episode of variability also, we have discussed in very detail about variations and its impact on device performance. Clock is important for a chip. Also, that clock can be generated on chip or off chip. There are two types of generation. Off chip clock generation is done using crystal and oscillator circuit, and on chip clock generation is done using PLL or DL. Now, routing a single clock around the chip is difficult issue. Another issue, if we use multiple clock, so if we use single clock, routing that signal across the chip with billions of gates is a tough work. It's a difficult issue. Another difficult issue, if we go for multiple clocks, then those clocks, their synchronicity is a thing. Clock signal might come at different times. So that delay between them is a tough thing to handle or control. Now, depending on applications, there are many timing components. Most common timing components are crystal oscillator, clock generator, voltage control oscillator. So this is a crystal. It's used to generate a single frequency. Crystal uses a piece of quartz which is cut at a particular angle and mounted on protective metal casing. It provides a frequency output when an electrical signal is applied. Piece of quartz which is cut at a particular angle and mounted on a protective metal casing. It provides a frequency output when an electrical signal is applied. Now, crystal oscillator. Crystal oscillators integrate the crystal with oscillator circuit, enabling the oscillator to provide higher frequency output. Now, clock generator. Clock generators are integrated circuits that generate multiple output frequencies from a single input frequency, which is a reference frequency. Crystal generate a single frequency. Crystal oscillator integrate the crystal with oscillator circuit. clock generator these are integrated circuits that generate multiple output frequencies from a single reference frequency. And then comes voltage controlled oscillators, a self-contained oscillator that varies its output frequency in concert with different voltages from a voltage reference. So these are 4 parts. More parts are there. We will move to the next slide. More 2 components are clock buffers and jitter annuator. Buffers are basically ICs for distributing multiple copies of a clock to multiple ICs with the same frequency requirement. And jitter annuator or jitter cleansers are clock generators with specialized circuitry for reducing jitter. Jitter is, in one sense, we can call it's a parameter. At the same time, it's basically a non-ideality. That's uncertainty of a clock signal. So we will see it in later slides. And we have already discussed in a delay episode. In this episode, in coming slides, we'll talk about jitter. Now, off-chip clock has limitations. So, these clock buffers and jitter attenuators. Off-chip clock has limitations like frequency is limited, multiplier is required, and uncontrolled clock phase synchronization issue is there. Now, PLL, which is an on-chip that can multiply the clock frequency. If clock multiplication is not required, DLL or DLL lock loop is used. So, this diagram is crystal oscillator it's going to chip 1, PLL digital system. Now, there is another chip. The main frequency is coming from this crystal oscillator and that is fed to one chip, that is to another chip. The way we have said. Now, PLL, these 2 diagrams, one is for PLL, this is of DLL. So, PLL uses an oscillator that creates a new clock, whereas the DLL uses a variable delay line that delays the input clock. A phase detector produces a signal proportional to the phase difference between the input and output clock. This is a phase detector, loop filter and VCO, and there is a feedback path. Programmable divider. In DLL, there is a low pass filter and a delay line. So, a phase detector produces a signal proportional to the phase difference between input and output clock. A loop filter converts the phase error into a control signal. A voltage controlled oscillator creates a new clock signal based on the error signal. This is about PLL. Now, in a DLL, same principle, but instead of changing the frequency, it just delays the clock until the phase is equal. That is delay lock loop. This is all about off-chip and on-chip clock generation. So, we are done with this slide. We will move to the next slide. Challenges of clock network. This is the first slide on the topic. This is the diagram. If you remember, we have already referred to this diagram in variability episode. What are the challenges of clock network? First is process variation. Variability due to device structure and other parameters lead to wafer variation. Due to this process variability and variations we are talking about in this slide, I have included this diagram. As we know that IC or chip or devices, they are manufactured in batches. And even we try our hardest, no 2 batches or no 2 wafers, or even, matter of fact, no 2 die within same wafer are absolutely identical to each other. There is some variation in dose, in energy and temperature during a process. As a result, the doping or oxide thickness, these parameters which are dependent on temperature, operating temperature, dose or energy, this gets a little bit varied. Even in a chip, one transistor from this side corner to another transistor to that corner are absolutely not identical to each other. So their performance are little bit varied. That is variation. Variability due to device structure and other parameters lead to wafer-to-wafer variations. The direct impact of process variations is on the yield and the performance of the design. The variations in the standard cell result in the mismatch across the various clock trees in the clock network. Due to variability, these parameters lead to wafer-to-wafer variation. From one wafer to wafer, there is variation in performance. The direct impact of process variation is on the yield and performance of the design. The variations in the standard cell result in mismatch across the various clock trees in clock net. Now, power supply variation. Supply voltage scaling causes variation in switching activity across the die. The uneven power dissipation across the die is the result of fluctuation in demand of current over a short interval of time. Ripples or noise voltage is induced in the supply lines due to presence of parasitic inductance. Parasitic inductance is there for state-of-art chips. Obviously, that's there. We have already discussed about on-chip inductance in interconnect series. The current flows in the chip via interconnect, which has a finite resistance And this resistance of the material, that has a deep impact on the performance. So the variation in the resistance lead to higher drop. Clock is also a signal. Whatever we draw in our digital clock as this, it's basically a signal, 1-0 sequence. And the signal means voltage level. Current is flowing through the wires. This is the practical impact. Now temperature variations. Temperature varies continuously on the chip while it's operating due to the power dissipation on the chip. Power dissipation is there. Obviously, junction temperature will increase. With the increase in temperature, the drain current decreases. Both device and interconnect depend on temperature and hence are affected by the variations in the temperature. How temperature can impact, we have discussed it in reliability episode. We have discussed it there. So now let's move to the other challenges of clock network. Signal integrity issue, timing violations, and design complexity. We have included this diagram because we are talking about signal integrity issues. Signal integrity issues include crosstalk, EM, IR. Crosstalk means interaction of when two parallel conductor lines or interconnects, they are running parallel, and in between it's not a free space, it's a dielectric layer. So it's working as a capacitor. That thing is crosstalk. The relative pitching of wires on account of capacitive coupling results in crosstalk noise. With increase in the clock frequency rates, the capacitive coupling dominates and results in significant delay in data paths. If wire resistance is very high or the current through the transistor is higher than estimated, there is an unwanted voltage drop. This unpredicted drop causing time degradation in the signal and clock nets. It produces unwanted clock skew in the design and hampers the signal integrity of the design. We need to save the clock network from the signal integrity issue. Now, timing violations. A design consists of millions of gates and multiple clocks. Timing violations due to setup and hold, clock skew, and due to signal integrity issue cause hindrance towards the timing closure for a design. There are multiple things. Of gates, very long path for signal to traverse, signal integrity issue, setup, hold, clock skew. These all types of timing violations may happen and we have to take care. So these are the biggest challenge for a proper timing closure of a design. Now, design complexity. Modern designs have millions of cells and the single chip is broken down into hierarchy of modules. The timing budgets are created for whole design, which permits the engineers to use hierarchical design methodology and work on their module for timing closure. Multi-stage clock gating structures are helpful for CTS. Multi-mode and multi-corner scenarios increase with the technology proceeding towards few nanometers. Therefore, timing closure as well as clock network have become challenge to the SoC designer. A huge number of gates there. Timing closure we have already talked. Another is multi-stage clock gating structures are there. We have already discussed about multi-stage clock gating in our clock gating episode. So many types of things are happening in a same chip while it's working. That is becoming very challenging thing. SoC designer need to keep all these things in mind. So this is clock source. This diagram is basically showing the latency. So if this is the scenario of a clock source to simple two flip-flop situation, just think what it can create when there are millions of gates, millions of flip-flop. How complex that structure, how complex that interconnect network can be. And this complexity is increasing because the application we want at consumer level, the application we want, that is becoming more complex. And again, nowadays, these mobile devices has become so popular, they rely on battery life. So again, we have to think about power management. There is a constraint on how much power you can spend. So this making the things more challenging. We are done with this slide. We'll move to the next slide. Now, clock parameters. Here we'll talk about 4 parameters. Later we will see these are basically non-idealities also. We can call them non-idealities. Clock skew, jitter, latency, and slew. The first, clock skew. We have already discussed about clock skew in delay episode. Clock skew is defined as the difference of insertion delays of two clocks belonging to the same clock domain. There are two flip-flop, same clock domain. So when clock is coming from clock source, there is a difference because we can see it's a very simple representation. Also, it will work. Like if clock source is this side, we can easily see that this path is shorter, this is moderate, and this is the longest. Clock signal it will be delayed to reach here and here compared to this flip-flop. If that is the clock, so at flip-flop 1, there will be delayed, this much delay. At 2, delay is there. That is clock skew. There are two types of skew, local or global, and value could be positive or negative. Local skew is the difference of insertion delays of two communicating flops of same clock domain. In a same clock domain, there are two flip-flops which two are communicating, and there is a difference of insertion delay or when it will reach those two flops. So that is local skew. And now global skew is the difference between the delay times for earliest clock reaching flip-flop and latest clock reaching flip-flop for same clock domain. That is the global skew. Now if capture flop receives the clock signal late than launch flop, then it results in positive skew. And similarly, if the launch flop receives the clock signal late than the capture flop, then it results in negative skew. They are communicating, and for signal transmission or data transmission, clock is required in two cases. Suppose data is going from here to there and clock is first coming here and going there next. So that is basically positive skew. And capture the launch flop receiving the clock later, that is negative skew. That is all about skew. Now we will see what jitter, latency and slew. Now jitter, latency and slew. So clock jitter is defined as the deviation of a clock edge from its ideal position in time. We are expecting with time, that is the clock signal. This rising edge and falling edge, that may vary with respect to time, its position. So if that is ideal clock with jitter will behave like that if we plot them against time. Now clock jitter is uncertainty in the clock edge. The cause may be noise, a fluctuating power source, or interference from nearby circuits. There could be many things. Noise might be there, power source might fluctuating. Interference from nearby circuit can also happen into such situation. Jitter can occur in both directions, positive or negative. Can be modeled by adding uncertainty regions around the rising and falling edges of the clock waveform. Clock jitter can be cycle to cycle, period, or long-term jitter. Clock latency or clock insertion delay, defined as amount of time taken by the clock signal in traveling from its source to sinks. That is clock latency. This is the clock source, this is the clock divider, and it's so clock source to clock divider, that's source latency. And now from clock divider, it's distributed in the network. So that is from the end flip-flop, that latency, the time taken, that is network latency. Clock latency is source latency plus network latency. Now clock source latency is defined as the time taken by the clock signal to reach the clock definition point from clock source. That is the definition point and that's the source. Time taken by the clock signal to travel from clock source to clock divider is clock source latency. And clock network latency or network insertion latency, that is defined as the time taken by the clock signal in traversing from clock definition point to the sinks of the clock. So this is the network latency. So altogether total latency is source latency plus network latency. And another point is slew. Whenever we draw a signal, clock signal, it's like this. Sharp rise, sharp fall. In actual, it doesn't happen because even that rising takes some time. Ideally, we measure this clock cycle like this. In practically, we don't do that because the signal doesn't look like that. Slew is defined as the time taken to change the state of the signal from 0 to 1 or 1 to 0. So here it's 0, here it's 1. That's not instantaneous. A certain time is taken here, that is slew. Here also 0 to 1, that is output with respect to this input. Slew is defined as the time taken to change the state of the signal from 0 to 1 or 1 to 0. If switching is very fast, this rise is quite sharp and this time is less. And if switching is not that sharp, that will be like that and it will take more time like this. So we are done with this slide. We will move to the next slide. So clock parameter and their impact. Now every practical clock has parameters like skew, jitter, latency, slew, etc. which are also their non-idealities. That should not be. Ideally, we don't consider them. Actually, they are present there. Reasons behind skew and jitter: clock generation, manufacturing device variation in clock drivers, interconnect variations, number of buffers, device variation, wear length and variation, coupling, load. These all could be the reason. Interconnect variations. There are three basically reasons: clock generation, interconnect variation, and environmental variation. Environmental variation is always there present because we are designing a chip to work in a practical situation where power supply might vary and temperature can vary. So clock generation, manufacturing changes could be manufacturing device variation in clock drivers. There are number of buffers, device variation, wear length variation, coupling load, interconnect variation. These are the reasons behind skew and jitter. Practical system to clock source when we are manufacturing, there are difference. So obviously their performance will have differences. Now, in two network interconnect variations are there. One clock is going, number of, depending on the buffers, how many device connected and their variations and wear length variation, all things are taken in consideration. We have to consider all the things. Now, clock skew and jitter can limit the performance of a digital system. We know that. Obviously, designing a clock network that minimizes both is important. Now, how to control non-idealities? These are non-idealities. These are the impacts. Performance may degrade. So, how we can control them? Now, balanced path. H-tree network, matched RC trees can eliminate skew. What are these H-tree network, matched RC trees? These are how we design the path, the network of the clock, how they are connected to the devices. EDA tools can perform that. So, H-tree network, matched RC trees are like that. Clock grids used in the final stage of clock distribution network that minimizes absolute delay, not relative delay. If paths are perfectly balanced, clock skew is 0. Distributed buffering reduces absolute delay and makes clock getting easier, but is sensitive to variations in the buffer delay. Shielding clock wires to minimize or eliminate coupling with neighboring signal nets. Might be interference from neighboring signal net control or impact the clock signal, so we can shield them. Distributed buffering reduces absolute delay and makes clock getting easier. How buffers are distributed, that is also an key point. Now keep close an eye on temperature and supply rail variation and their effects on skew and jitter. So we have to consider that. Now power supply and noise limits the performance of clock network. So these are the points we need to check. We need to keep an eye on all of this. So we are done with this slide. Now we will see what are these clock network. Now clock network. There are 4 points on this section: conventional clock tree, clock mesh, H-tree and fishbone, and multi-source clock tree system. Now, conventional clock tree distribution. Single point CTS is the choice for designs when frequency is lower and number of sinks are less. So, it's a conventional CTS. This is clock source. Now, these are the clock tree cells. This zone. After that, clock gates and buffers. And finally, these are the loads. So, as name suggested, having single clock source which distribute clock to every corner of the design. This is the single clock source. In single point CTS, the point of divergence lie at the clock source. So, it shared very large uncommon clock path, more susceptible to OCV variation. Common path is very less. Uncommon path is very large. And this process is more susceptible to OCV variation, on-chip variation. So what is OCV? We already have a episode on that. You can get to know in details. Watch that episode. Clock gates are strategically placed near source, saving large amount of dynamic power. What are the advantages of this distribution? Simple to implement, very simple structure, better clock gating, reducing power dissipation. And disadvantages? Higher insertion delay, more uncommon clock path, more prone to OCV, tough to achieve lower skew due to asymmetric distribution of sinks. Conventional CTS is not a good choice for high frequency signals having high number of sinks all over core region. Implementation is easier, although very prone to OCV. Quite good at reducing power dissipation, better clock gating, although there are some issue for also not good for high frequency signals, and it's really tough to achieve lower skew because of asymmetric distribution of sinks. So this is the conventional clock tree. We are done with this slide. Now we will move to clock mesh. So this is clock mesh, another type of clock network. Clock mesh is divided clock domains into many grid areas. Clock signals connect to the clock mesh node through pre-driver buffer chain. This is clock source, pre-mesh driver. Now mesh driver, this is before the pre-mesh distribution. This is a mesh net, and mesh these are the drivers for mesh, and clock gates and receivers are on the other side, and finally loads. The global mesh use 2 layers of metal wiring crossing each other in order to spread the clock signal that placed by top level chain to the whole clock domain and will control clock skew and clock delay. So distribution scheme is different from the conventional one. There is a network of pre-mesh drivers to drive the clock signal from clock port to input mesh driver. There is a clock network. This is source and these are mesh drivers. So there is a network in between that drives the clock signal from source to this mesh driver. The output of all mesh drivers will be shorted using metal mesh, which will carry the clock signal across the block using horizontal and vertical metal stripes. In mesh structure, power dissipation is high as clock gate cells are inserted after the mesh net, so clock gating is done at local level only. Advantages: lower skew, highly tolerant to on-chip variation, and possible to achieve lower insertion delay. Disadvantages: more power dissipation and difficult to implement. Structure is complex. It's more power hungry basically. So power dissipation is more. Dynamic power dissipation in this structure is more, although OCV on-chip variation is less and delay is less. So these are two structures. We are done with this slide. We will move to the next slide. Now H-tree and fishbone. The H-tree structure is highly symmetrical. The pre-drive buffers evenly distributed on the trunk, and it can manage clock skew for the clock domains with a large number of flip-flops. H-tree structure consumes more routing resources while there will be more power consumption. So this is H-tree structure, it's a symmetrical in structure, and this one is fishbone. In fishbone, this way, because of this structure, it's called fishbone. This is a fishbone structure, and there are more different structure, like this is tree, as we can see, this is X tree, this is H tree, like this, and tapered H tree. These are 4 different topologies. And now finally, multi-source clock tree system. MSCTS is a hybrid system containing the best aspects of a conventional clock tree and pure clock mesh. It's a hybrid system between conventional clock tree and a pure clock mesh. Now, clock mesh delivers the best possible clock frequency, skew, and OCV results, and whereas conventional clock tree delivers the lowest power consumption and the easiest flow. So, multi-source CTS offers a compromise between the two methods while favoring the OCV tolerant nature of pure clock mesh. A MSCTS design comprises of 3 different structures in the design. One is pre-mesh clock tree, multi-source mesh fabric, and moderately sized clock tree. Now, what are the benefits? Better performance and lower skew than conventional CTS. That is clock tree. Now, better OCV tolerant than conventional clock tree, better multi-corner performance than conventional clock tree, less power consumption than pure clock mesh, and greater tolerance of irregular, highly macro density designs than pure clock mesh. Faster and easier flow than pure clock mesh. It's taking benefit of both the structure, conventional clock tree and clock mesh. Now, pre-mesh clock tree. We have seen there are 3 parts. So, first, pre-mesh clock tree. This is the clock route. Now, this is pre-mesh clock tree. And here, coarse mesh is there. And after that, multi-point drivers and subtree is there. So, each buffer in the pre-mesh tree drives 4 other buffers. That's pre-mesh topology similar to H-tree placement and routing. H-tree structure is uniform, scalable, predictable method to distribute root clock over a large area. Also tolerant to corner variation because of their balanced structure. So that's pre-mesh clock tree is like conventional clock tree. Now, multi-source mesh fabric. The multi-source mesh fabric resembles a power ground or clock mesh fabric, although less dense. The coarse fabric smoothes out any remaining clock arrival time differences from multiple H-tree buffers that directly drive the fabric. The mesh skew at the mesh plane is effectively 0. So, multi-source mesh fabric is there. Its resembles a power or ground or clock mesh fabric, also less dense, and coarse fabric smoothes out any remaining clock arrival time differences from multi-H-tree buffers that directly drive the fabric. And the measured skew at the mesh plane is effectively 0. And now finally, moderately sized clock trees. Multiple clock trees that are attached to the coarse mesh. There is a multiple clock tree that are attached to the coarse mesh. That structure gives the technology its name from multi-source clock tree system. It's a local network, multi-point drivers are there, integrated clock gating is getting done here, and this is the subtree. So that is multi-source clock tree system. After mesh, there is a subtree, so that name comes from this structure. We are done with this slide and we are done with this today's episode that we had all about clock tree in VLSI.
Hey guys, welcome back to the computer screen. In today's episode, we are going to discuss the below points. Introduction. We'll do a general introduction to the clock tree synthesis scenario. Next, we'll talk about CTS position in the entire VLSI design flow. Next, we'll go in detail what is CTS. With infographics, we will understand the pre and post CTS scenarios with respect to the clocks, buffers and flip-flops. Next, we will mark the different levels that occurs during the CTS. That means these levels were not there when the CTS process has not happened. Next, we will go into the PTS methodologies that are used in VLSI design. Next, we will use infographics to understand what are the steps in common EDA tool for CTS. That is the menu for today. So without any further delay, let's begin. Introduction. The clock distribution and routing is important in digital design as it impacts power, performance and area, sometimes known as PPA of the SoC design. Next, the clock tree synthesis CTS process impacts maximum operating clock frequency to the clock skew. What is a maximum operating clock frequency? It's nothing but the frequency that your design, that means when it is in chip, that can operate. Process variation generated race around conditions are avoided through CTS. This is a very important point. When we have a process variation, we have an entire episode on process corners. There we have talked about the process variation. The link is provided in the description. Please go ahead and watch in case you do not know about the process variation. The process variation generated race around conditions are avoided through CTS. We'll go in detail in later slides. In test mode, many flip-flops are hooked together from a scan chain. What is a scan chain? This is formed in the DFT process of the entire VLSI flow, and this test mode is enabled for the testing, that is the design for testability, which is the DFT. The skew requirements of a scan chain are patterned for the scan clock tree as every path during the test mode is a short path. The clock tree network is responsible for significant amount of power dissipation as it switches most frequently. So one thing here to be very much precise, that the clock tree which is synthesized to give a good contribution towards the power consumption of the entire chip, because this particular area of the nets, the clock nets, has to operate even though any particular block is off. That means this has to operate at any condition. So this is very much responsible for significant amount of power dissipation. Clock trees are good candidates for low power VLSI designs. We have entire episode on low power VLSI design. The link is provided in the description. In case you have not watched, please go ahead and watch that, and that will explain why the clock tree is a good candidate for the low power VLSI design. Here we are done with our introduction. So let's move on to the next slide. CTS in the entire VLSI design flow. So here when we talk about the VLSI design flow, we mean that this is the ASIC design flow or the SoC design flow, because in analog designs there will be no clock. So let us begin our VLSI design flow and let us see in which position the CTS is there. That means the clock tree synthesis is there. Design specification. Here in this direction we will proceed. Design specification is the first step where we write our specs, maybe in pen and paper or maybe in computer notepad or WordPad or maybe in MS Word. Next, we proceed towards the RTL coding, which we begin with the Verilog or VHDL or System Verilog kind of languages. Then comes the verification. This is the digital verification of the coding that we have written. Next comes the synthesis. Once all these steps are done, and if needed, if these are iterated together, then once this is freezed, we proceed toward synthesis. Next comes the DFT and the scan chain insertion process. This is for the DFT verification of the chip, whether it is for the simulation or whether it is post-silicon. So this has to be finalized here in the DFT step. Next comes our floor planning. So here up to this point, we are in the front end part. And here from the floor planning, we are entering into the backend. Next comes the power routing planning stage. Next comes the global placement. Next comes the detailed placement. So here we have done the planning, right? Now all this planning has to be executed. So these are the executions. Next we have clock tree synthesis, and now in right hand side we will proceed in this direction. Next we have global and detailed routing. So whatever plan we have done here, right, in this stage, we have to do the placement here, and then we have to do the global, power and detailed route. Every routing is done here. Next comes the layout generation or necessary changes. So any particular stage is not done in one particular instance. So sometimes they have to get iterated, right? So they have to iterate multiple times. Any step, you see steps here. Any step has to be iterated multiple times to achieve the perfection and less error or zero error, whatever is there. So for that, it has to be iterated multiple times. Whatever process I have told you here in the entire line, or here you are going to see here in this direction, all of them are iterated multiple times. Next comes the DRC and LVS. Next comes the parasitic extraction, that is PF extraction. In case you are having an ASIC, or in case you have a block, you can have a DSPF. Next comes the static timing analysis. This is post layout STA. We have an entire episode on STA. Please go ahead and watch that in case you are interested in static timing analysis. Also there we have talked about different file formats including the parasitic, this PEX. And then we move on towards the EM and IR verification. This is also dependent upon these particular extraction results. And then we proceed toward LEC and final tape out checks. LEC means the layout equivalence check. And finally, we are ready for tape out. So don't think any step happens in one single go. Each step has to be iterated multiple times. Maybe these two are interrelated. So the iteration will happen in between these two. Or in case it has to go back up to this planning stage, right? It has to go back planning and then it has to come back. So any of the stages here has to be iterated multiple times. In today's episode, we will focus on clock tree synthesis. And we know it stands immediately after the planning and the placement. Here is the planning and placement. So after that, before the routing begins, we have the clock tree synthesis. So we are done with this particular slide. Let's move on to the next slide. What is CTS? Now we have talked about CTS, the scenario where it is used. Let us understand what is CTS. Clock spine routing scheme with all clock pins driven directly from a clock driver. So clock driver is nothing but like PLL kind of circuit in the digital chip or a Xtal that produces the clock. So that is the clock driver, and the clock spine I will explain in the next infographics where we will see, right? FPGAs are often used in this fishbone type of clock distribution scheme. Here we talked about FPGAs, although we have in ASIC a clock spine for a gate array. It is needed. The clock spine is nothing but the main branch that is distributing the clock. A clock spine for cell-based ASIC. Typical chips have thousands of clock nets. A clock spine is usually driven from one or more clock driver cells. Delay in the driver cell is a function of the number of stages and the ratio of output to input capacitance for each stage. It is called taper. Clock latency and clock skew. An engineer tends to minimize both latency and skew. So these terms are well explained in the STA series. Please go ahead and watch them. You will find the chapters so you can directly navigate to the particular section where these are explained. What is CTS? We have briefed here. Let us see what happens in CTS. We are done with this particular slide. Let's move on to the next slide. Pre and post CTS we will explain with infographics. So this is pre-CTS stage. We have a clock root, that means it may be a Xtal or maybe a PLL. Whatever we have, right? Generally in circuits we have PLL as a clock driver. That means the clock root. And without CTS we have a direct connection and branches like this. So they go to the end leaf cells, that is the flip-flop. After we have the CTS, what happens that there are multiple buffers are inserted in between so that the proper power management and the levels of the clock are maintained. In case you have a clock gating here, right, somewhere. So here we are having the plain buffers, right, but however we can have clock gating. So clock gating I have explained in the episode, and the link of the episode is given in this description of this video. In case we have a clock gating, so that will also appear in this particular tree. So here we are done with the simple diagram. Let us zoom into this one, how different levels are there and what are they named. Various levels during CTS. So here we have drawn the same picture, however we have separated each of the section. So this one is the clock source. This is called the clock source or clock root, from where all the clocks are generated. And next level is the driver, level 1 driver. These are the level 1 drivers. These are planned and inserted through the clock tree synthesis. So this synthesis happens during the CTS. Next we have the second level of drivers here. These are the end product of the CTS. At last, we have the leaves, that means the receivers here. The clock tree synthesis actually insert this level, and in case there is some clock getting here, it will be also insert. So you can see that from 1 and 2, these two levels, two more levels or more than two levels are inserted through the CTS. The complexity of modern age, that means now we are in the sub 45 nanometer range, or rather we can say sub 10 nanometer range. The complexity and the levels are too much in the CTS. So here we are done with the infographics explaining what happens, what levels are inserted in CTS. Let's move on to the next slide. CTS methodology. Now here in this slide, we will talk about the different methodologies that are used for CTS. These may be done by a designer, or these may be they are already existing in a tool. However, some methodologies are behind the CTS. We will just touch base on them. In order to reduce the iteration and TAT means the turnaround time, clock tree designs methodologies are developed by engineers. This can consist of sub-steps, that means the design of the tree structure, layouting of the clock tree, synchronization of multiple trees of the same clock source, and there could be clock gating. In detail, the steps can be generate netlist with specific number of receivers in the clock tree, design of the structure from bottom-up process. Bottom-up means you have a design from a top view, but however, this is developed from the bottom. That means the leaf cell is designed first and then we proceed towards the different levels. So these methodologies have to be developed first and then implemented through CTS. Use of the layout tool features to form the clock tree. That means the clock tree has to be formed. For that, we have to use the layout tool with the methodologies we are preparing as engineer or which is provided with the EDA tool. To analysis of delay and skews of all clock nets. Iterate with correction until the target is achieved. Just to have the turnaround time, we have to iterate multiple times. So that is the main thing of any VLSI process step. Any step in VLSI design has to be optimized until the goal is reached. So here we are done with the methodologies that either an engineer does or they exist in the EDA tool, or the combination of both, or some improvisation or new methodologies, those are implemented. However, this is the basic thing that happens in CTS. So here we are done with the CTS methodology. Let's move on to the next slide. CTS in EDA tool. Here in this slide, we will use the infographics. These images are taken from internet. So please don't expect a tool demo after this one. So here in our commonly used EDA tool, what we will have the option for the clock specification file. In case you don't have, say your engineer do not have, you can use the gen spec to generate one. So generally it is called a clock tech file, TS tech or C tech. This kind of extension will be there, and these will be the output directory. And once you are done, you have to click on OK. In case you are not done, before this all the steps are done in the EDA tool. This image is for the CTS only. So here you can gen spec, or in case you have a handcrafted CTS tech file or CTS file, you have to use this button to load it here in this, and this will give the output direct. And once you are done with these two, you click on OK, or you click on apply and then click on OK. Once you are done with this window, the next window comes like this. So you can see here the library is there, and here the buffer and inverters will be there. So you can see, and you have to pick up the buffer or inverter, whatever you want to include in the CTS tree. So those you have to handpick. Nowadays complexities are there, so there could be different kind of buffers and all. Those have to be there. And in case you have an output specification file, that has to be pointed through this. So once you are done, you have to click on apply and then OK, or simply on the OK. You can see these two images are different here in the even in the title bar, right? So these are picked from internet, you can understand, but however for your understanding you will have these things, and whatever methodology is behind there you will understand once you run these things in your actual EDA tool. Here we are done with this particular slide. Let's move on to the next slide.
Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and specialized routing. This is the third episode in routing in physical design, and we have already covered global and detailed routing. Now it's time for specialized routing. Next, area routing, key objectives and optimization factors. Next, basic concept in clock networks. After that, delay in clock networks, clock skew and clock routing problems, modern clock tree synthesis techniques. This is the first slide on this topic. Next, another slide on modern clock tree synthesis techniques. And then MMM versus RGM. These are two methods. There is a comparison between them. Then modern clock tree synthesis techniques. This is the third slide on the topic, and clock skew optimization and power trade-off, first slide, and clock tree optimization and power trade-off, second slide. So these are the pointers we will discuss in our today's episode. We are done with this slide. Now let's move to the next slide. Design flow and specialized routing. This diagram we are using for last few episodes, and today also we will take reference of this one. Once the flow enters physical design, there are multiple steps like partitioning, chip planning, placement, clock tree synthesis, signal routing, and finally time enclosure. So in signal routing, we have already covered global routing and detailed routing, and today it's time for specialized routing. In digital integrated circuit, first signal wires undergo global routing and then followed by detailed routing. We all know that. However, in certain designs such as analog circuits and printed circuit boards, that is PCBs, with gridless routing or trackless routing, this distinction is unnecessary. It doesn't need this. Similarly, older or smaller designs with one or two metal layers also fall into this category. For this type of routing, we take specialized routing. Now, when global and detailed routing are not handled separately, area routing is used to directly establish metal connections for signal routing. Unlike routing with multiple metal layers, area routing prioritizes minimizing wire crossing. Clock signals require special consideration. This is the basic about specialized routing. We are done with this slide, and now let's move to the next slide. Area routing, key objective and optimization factor. We have already mentioned about area routing. When there is a discrimination between global and detailed routing is not required. Overall, it's done by area routing. Objective, area routing aims to connect all net while bypassing global routing, operating within the available layout, pace, adhering to geometric and electrical constraints. So that is global routing. Minimize total routed length and number of vias, optimizing wear area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. So these are optimization goal. Minimize total routed length and number of vias, optimize wearing area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. Now, constraint considered, technological constraint like number of technological constraints like number of routing layers, wherewith electrical constraint like signal integrity, coupling effects, geometric constraints like preferred routing direction, wear pitch, etc. So these are the constraints. What are in number of routing layers, wherewith these are technological constraint. Now, electrical constraint like signal integrity, coupling effects, and geometrical constraint like preferred routing direction, wear pitch. Three types of technological constraint, electrical constraint, and geometric constraint. Now, impact of net ordering. The sequence of net routing affects efficiency and runtime. Greedy wear length based routing can cause inefficiencies, and multi-pin net require careful decomposition and ordering. That is impact of net ordering. In which sequence net ordering is done that affect the efficiency and runtime, and greedy wear length based routing can cause inefficiencies. So now net and pin ordering strategies. Pin ordering use Steiner tree based algorithm to convert multi-pin nets into two-pin nets, sort pin locations by X coordinate, and connect from left to right using shortest path algorithm. And net ordering challenges. Finding optimal net order is complex. Infactorial possibilities are there. Now, net ordering rules are there. Nets with larger aspect ratios are routed first. If aspect ratio is the same, the shorter net length is prioritized. If a net's pins are fully inside another net's bounding box, it is routed first. The net with fewer interfering pins in its bounding box is routed first. Ties are resolved based on total pin count inside the bounding box. These are the rules followed. So this diagram is showing there are two ways to connect this net. There are two ways. It can be routed this way, can be routed this way also. Now there are 4 nodes and two nets are mentioned, like A and A. These net can be connected this way, these two, and these can also be connected this way. It's shown two different ways of connection in both the diagrams. So we are done with this slide. We will move to the next slide. Basic concepts in clock networks. Most digital designs are synchronous, that is, computations occur in sync with the clock signal. The clock ensures that internal state variables and inputs are processed correctly through combinational logic, generating new outputs and state updates. The clock signal, often called the system's heartbeat, can be generated off-chip or by on-chip analog circuits like PLL and DLL. Its frequency may be divided or multiplied depending on the need of the different circuit blocks. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all parts of the circuit receive the clock simultaneously. So this is the main focus in case of clock tree. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all part of the circuit receive the clock simultaneously. Now, a clock routing problem involves connecting n+1 terminals. A clock routing solution consists of wire segments that connect all terminals, ensuring the signal from the source reaches every sink. This solution has two key aspects: topology and embedding. So clock routing problem involves connecting n+1 terminal, and clock routing solution consists of wire segments that connect all the terminals, ensuring that signal from source reaches every sink. This solution has two key aspects. One is topology and another one is embedding. Clock tree topology are rooted binary tree G with n leaves representing the sink's internal node, include the source and any additional Steiner points, and embedding defines the exact physical placement of edges and internal nodes in the topology. Figure A illustrates a 6-sink clock tree instance. This is a 6-sink clock tree. There are 6 sinks, and figure B shows its connection topology. So connection topology, it's a rooted binary tree with n leaves. So S1, S2, S3, S4. There are n number of sinks, so n number of leaves. This is the clock tree topology. And embedding, figure C presents a possible embedded clock tree solution. It's a possible embedded clock tree like S0. From there, this connection is going like that. S0 to S1 and S2, that is U1, this one. Now U2, U3, U4. From S0 it's coming to U2, from there U3 and U4, and from U4 S5 and S6, and U3, S3 and S4. So this is the embedded clock tree solution, and this is the clock tree topology. We are done with this slide. We will move to the next slide. Delay in clock networks. Signal delay is the time a signal takes to switch states, that is low to high or high to low, as it travels through a routing tree. It starts at logic gate outputs built from nonlinear transistor and moves through wires and vias which add parasitic effects. We all know about parasitic effects of wires. In our interconnect series, we have discussed that parasitic effect in detail. Now, exact delay calculations are complex, so tools like SPICE or prime time are used for precise sign-off delay measurement. However, place and route algorithms use approximate models such as linear and Elmore delay models. Linear delay model. In the linear delay model, signal delay between nodes I and J is proportional to the path length in the routing tree, independent of connection topology. The normalized linear delay between nodes U and W is sum of edge lengths along the path. On-chip wires have both resistance and capacitance, which increase with length due to RC effects where delay grows quadratically, which the linear model does not capture. Despite this, it remains useful in design tools, especially for older technologies with lower drive resistance and wider wires. Its simplicity makes it widely used in EDA software. Linear delay model, although it's a linear model, and when RC comes into play, the wire delay increases or grows quadratically. it's a quadratically increasing and we are trying to model it through linear delay model. It's not appropriate, although it's a good assumption because it's a simple model and it's very useful for older technologies with lower drive resistance. And L-mode delay model, the L-mode delay model we have already discussed in interconnect series in the delay episode. The L-mode delay model provides a more accurate delay estimate by considering resistances and capacitances in the routing tree, especially for modern circuits with significant RC effect. Physical design tools use L-mode delay approximation for three key reasons. First, it considers the effect of off-path wear capacitance on sync delay. Second, it provides a good balance of accuracy and correlation with circuit simulator estimates. And third, it can be computed efficiently in linear time using two depth-first traversals, one to determine capacitance below each node and another to calculate delays from the source to each node. It's considered downstream and it's upstream. These are the leaf like a tree. Current flow from this direction to that direction and the current out this way. The calculation is done. We have already discussed in detail in our interconnect series. Link is provided in the description. You can take a look if you want the reference of L-mode delay model. Delay in clock network is basically calculated by linear delay model, which works quite efficiently for older nodes, and L-mode delay model is much more accurate approximation. We are done with this slide. We will move to the next slide. Clock skew. There is one episode, different delay types in VLSI. There also we have discussed about clock skew. Clock skew is a maximum difference in clock signal arrival times between sinks. So clock skew and clock routing problems. We have already discussed about clock skew in one episode called different types of delays in VLSI. Link of that episode is provided in the description. You can take reference of that episode also, although the perspective a little bit different there. Clock skew. This is maximum difference in clock signal arrival times between sinks. Since the clock signal should reach all sinks simultaneously, minimizing skew is crucial for circuit timing. Ideally, clock should reach every sink at the same time, although it doesn't happen because the signal takes finite time to travel through the wires. Local skew. The maximum difference in clock arrival times between related sinks that are sequentially adjacent, meaning there is a combinational logic path between them. Usually there is a clock, there is a sequential block and then some combinational blocks are there, so it takes some time to travel. So local skew is the maximum difference in clock arrival times between related sinks, that is sinks that are sequentially adjacent, meaning there is a combinational logic path between them, that is local skew. And now global skew, the maximum difference in clock arrival times between any two sinks, whether related or not. It is difference between the shortest and longest source to sink path delays in the clock tree. In most cases, global skew is what is referred to as clock skew in design analysis. So that is a maximum. If that is the clock and there is the closest sink present is there and the farthest is here, the skew from these two, the time difference in reaching this sink and that sink would be different, and that is the maximum difference when it's reaching the shortest path, covering the shortest path and the longest source to sink path. Difference between these two delays in the clock tree, that is actually referred as clock skew in design analysis. That is the maximum clock skew and that is global clock skew mentioned at clock skew. There are few clock routing problems, like modern low power clock network design integrates zero skew trees and relies on SPICE for accurate circuit simulation. Zero skew tree ZST problem. A ZST ensures that the clock signal reaches all sink at the same time. That is zero skew. No skew is there. Skew is defined using a delay estimate like linear or L-mode delay. Bounded skew tree or BST problem. While ZST are useful in theory, exact zero skew is not practical due to increased wear length leading to higher capacitance and manufacturing variance, which cause difference in wear resistance and capacitance. Instead, real world clock tree allowed a small skew within a given bound. So ideally zero skew is not possible. So a small skew within a given bound, that is bounded skew tree, is acceptable level. A skew with an acceptable level is approved or allowed. Now useful skew tree problem. In some cases global skew control is unnecessary. Instead the focus is on local skew between related flip-flops or latches. Enforcing strict global skew constraint can overcomplicate the problem. So in some cases it's not necessary. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signals between flip-flops arrive neither too late nor too early double clocking. By optimizing sync arrival times, the clock period P can be reduced, improving circuit performance. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signal between flip-flop arrive neither too late, that is zero clocking, or not too early, double clocking. By optimizing sync arrival times, the clock period T can be reduced, improving circuit performance. There are two diagrams, that is minimal clock period time 0 nanosecond at 0 nanosecond, and after 2 nanosecond it's reaching here. After 6 nanosecond is reaching FF3, third flip-flop. So minimum clock period E equal to 6 nanosecond with 0 skew. And here skew is a little bit adjusted, like there is a skew of 2 nanosecond and it's reaching, and this one has 2 nanosecond skew. So if between these FF1 and FF2 there is a skew happens because of a combinational logic path is there, and for this path if the signal takes 2 nanosecond, so here when it's reaching FF2 it's basically 0 skew, and when it's reaching here in 6 nanosecond, so it's effectively becoming 4 nanosecond with 2 nanosecond skew. So minimum clock period becoming 4 nanosecond with 2 nanosecond skew. So we are done with this slide. We will move to the next slide. So now modern clock tree synthesis. This is the first slide on this topic. So clock trees are crucial in synchronous circuit design. Obviously everything needs clock signals. There have to be a clock tree and affecting both performance and power consumption. And a well-designed clock tree ensures low skew, delivering the clock signal to all sequential gates simultaneously. That's the requirement or the expectation from a well-designed clock tree. And after the initial tree construction, the clock tree goes through clock buffer insertion to strengthen the signal and skew optimization to further reduce timing variation. So that is the basic. Constructing tree with zero global skew. 5 early clock tree construction algorithms whose core ideas still influence modern EDA tools. These algorithms address different scenarios like builds a clock tree without considering exact sync positions, construct both the tree structure and physical layout simultaneously, and 3 is given a predefined topology determines its physical placement. So H-tree, the H-tree is a self-similar fractal structure that ensures exact zero skew due to its symmetry. It's built by recursively dividing a unit square. A central segment is placed through the root. 2 shorter perpendicular segments extend to the centers of 4 quadrants. This process continues until reaching all sinks. The H-tree is widely used for top-level clock distribution, but it has limitations like blockages can disrupt the pattern, irregular sync placement makes direct implementation difficult, and high routing cost. To reduce signal inflection, where tapering is used, where the width halves at each branching point. This is H-tree. H-tree has a symmetrical structure, although it has some cons, some downside. That's why where tapering is used, where width halves at each branching point. This is H-tree. We are done with this slide. We will move to the next slide. Modern clock tree synthesis. This is the second slide. Method of means and medians. The MMM algorithm proposed by Jackson, Srinivasan and Pu in 1990 improves on the H-tree by handling arbitrarily placed sinks. It follows a recursive approach like partition terminals into 2 equal subsets based on median. It's partitioning again, it's based on median. So these medians are connected again based on this median. It's divided in this way and this way and this way based on median. So many small rectangular blocks are there. This method is flexible and adapts to different sync distribution. While MMM can be simplified into an H-tree-like approach, it only minimizes skew heuristically. In the worst case, the longest source to sync path can be as large as the chip diameter, making the algorithm's effectiveness highly dependent on cut direction selection. And this is improvisation over H-tree. Although it has a downside like effectiveness of the algorithm depends on the cut direction selection. Now recursive geometric matching or RGM. The RGM algorithm introduced in 1991 is a bottom-up approach to clock tree construction unlike the top-down MMM algorithm. How RGM works, the algorithm finds a minimum cost geometric matching of n by 2 line segment, ensuring no two segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew between connected sinks. The n by 2 tapping points from one stage serve as input for the next matching step. The process continues until the clock tree is fully constructed. So here, clock tree structure started from median, here opposite. Any two adjacent sinks. So here algorithm was little bit different, like the algorithm finds a minimum cost geometric matching of n by 2 line segments, ensuring no two segments share an endpoint. No two segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew. So these 2 points are connected by this segment and these two segments are considered and they are connected. And in between there is a tapping point is found. These two segments are connected and there is a tapping point. So those tapping points, tapping point from one, there is a tapping point of these two, there is a tapping point of these two are connected. Now in these two between there is a tapping point and again tapping point from here. So these are connected like this, these are connected. Again these two are connected by this tapping point, these two sinks are connected by this tapping point, and these two tapping point are connected by another tapping point. This is the tapping point of these four final at this stage, and here these two, there is a tapping point, these two, there is a tapping point, and between these two tapping point there is another tapping point, and these tapping points are connected, and in between we find another tapping point and this tapping point, and here it means here meets here in another tapping point. It's a bottom-up approach and here it's top-down approach. So we are done with this slide and we will move to the next slide. Now let's take a look at the comparison of MMM and RGM. These 4 sinks and top-down approach. Median is found here. Again, 2 medians are found this way. And here it's a connected segment and tapping point, and these two. This tapping point and this tapping point connected, and this is the tapping point. So RGM improves clock tree balance and reduces wire length. So we can easily see wire length is reduced here compared to MMM. Above figure compares MMM and RGM for 4 sinks. If MMM selects a poor cut direction, RGM can cut wire length in half. However, like MMM, RGM does not ensure zero skew. If two subtrees have very different delays and their roots are matched, finding a zero skew tapping point may not be possible. This is the comparison between MMM and RGM. We are done with this slide. We will move to the modern clock tree synthesis. This is the 3rd slide on the same topic. Exact zero skew algorithm and deferred merge embedding. These two different algorithms. Proposed in 1991, the exact zero skew algorithm improves upon RGM by ensuring precise skew balancing using Elmore delay model instead of the simpler linear model. It uses Elmore delay model. Key feature, it calculates exact zero skew tapping point using the Elmore delay model, leading to lower actual clock skew in real designs. When merging two subtrees with different sourcing delays, it adjusts wire length to equalize the delays. During merging, the zero skew tapping point is carefully placed along the matched segment. It equalizes the delay by adjusting the wire lengths. When two subtrees with different sourcing delays are merged, the algorithm adjusts wire lengths to equalize the delay, because when clock signal travels through wire, some delay also added there. During merging, the zero skew tapping point is carefully placed along the matched segment. So these two are subtrees and this is the tapping point. So this length is calculated accordingly to balance the skew. And another method is deferred merge embedding. The DME algorithm improves clock tree construction by delaying the selection of merging or tapping points for subtrees. Unlike earlier method that fixed internal node locations early, DME optimally places these nodes later, ensuring minimal source to sink delay and minimal total tree cost. So how DME works, unlike MMM and RGM, which only require a set of sink location, DME needs a predefined tree topology as input. Key advantage, MMM, RGM exact zero skew fix internal node positions too early, limiting flexibility, whereas DME ensures more optimal placement of internal nodes, leading to better clock tree performance. Deferred merge embedding and improvisation over the previous algorithms. So we are done with this slide. We will move to the next slide. Clock skew optimization and power trade-off. This is the first slide. Key challenges: low clock skew is critical for high performance design. Clock networks consume significant power, requiring trade-offs between skew and capacitance. Accurate timing analysis is needed. All the simulations are time consuming. Closed form delay models are inaccurate. A common approach is to optimize using L-mode delay model and then fine tune with more accurate models. Now, clock tree optimization steps. There are multiple steps in that. First is geometric clock tree construction. Initial clock buffer insertion, clock buffer sizing, wear sizing, and wear snaking. So these steps account for process, voltage, and temperature variations. Now, high-level skew optimization. Earlier, a single buffer was enough to drive the clock tree. Now, technology scaling, multiple buffers are required. Buffer insertion ensures that clock signal reaches all sync efficiently. And Guineken's algorithm optimally buffers a tree to minimize L-mode delay that runs in n squared time, quadratic relation, and where n is number of buffer locations, and a faster O(n log n) variant improves scalability. Optimizations reduce skew, power consumption, and variability effects. So, skew optimization is very important. Now, clock buffer sizing. Initial buffer sizes impact later optimizations. Best size is determined experimentally, that is binary search. To fix skew between two sinks S1 and S2, identify the unique path between them. Upsize buffers based on pre-computed tables, and larger buffers improve robustness but increase power and delay. That is about clock buffer sizing. So now clock skew optimization and power trade-off. This is the second slide. This is a diagram. We have already used it in variability episode. So here process level, device level, circuit level, and chip level variability factors are mentioned. So wear sizing, wear width affects power and manufacturing variation. Wider wears are more resilient to variation, although the capacitance and power consumption both are higher. Thinner wears are used in low power designs where width can be adjusted dynamically based on timing analysis. Now, low level skew optimization focuses on local adjustment with higher precision. Techniques: wear sizing, that is adjust width for fine-tuned timing. Wear snaking, that is increase path length through delay fast signals. Wear detouring increases capacitance and resistance, so that slows down the propagation. Now, variation modeling. Process variation impact each transistor differently. Environmental factors, that is temperature, voltage fluctuation, affect performance. Now, two modeling approaches are there for Monte Carlo simulation, that is accurate but slow, and pre-computed lookup table, efficient and reusable. Captures worst case skew variation based on technology node, buffer wear library, and path length, variation model, yield, etc. That enables fast, accurate optimizations, that is buffer sizing. And what are advanced clocking techniques? Active deskewing and clock meshes, that is common in CPUs, and clock gating reduces power dissipation. These are advanced clocking techniques. We already have an episode on clock gating. Link is mentioned in the description. You can take reference if required. That is about specialized routing and clock tree routing. We are done with this slide and we are done with our today's episode. Now let's take a look at the pointers we are going to discuss in today's episode. First, power management and clock gating. Next, clock gated versus non-clock gated registers. Next, different types of clock gating. N-based and latch-based clock gating. Flip-flop and mux-based clock gating. Bus-specific clock gating. Optimized bus-specific clock gating. Local explicit clock gating. Enhanced clock gating. Typical clock gating circuit. Type and delay matching clock gating. Multiple stage clock gating. And finally, advantages and challenges of clock gating. So these are the pointers we will cover in our today's episode. Now let's move to the first slide. Power management and clock gating. In our second episode, in power optimization episode of this series, we have discussed about clock gating in a very simpler and basic way, and in today's episode we will discuss in detail. Now, clock gating is very effective in reducing the power consumption. Clock consume a lot of power. Every sequential component in a circuit require clock signal. So clock is present in all those registers and that's why clock consume a lot of power. Now this technique reduces power consumption by using a clock getter. Clock getter or turn off the clock that is driving a part of the logic when it's not required. It will not affect the original functionality of the design. When a part is not required, we don't let clock signal to reach that part of the circuit. When that is not required or that part is not in use, that time we just stop clock signal to reach there. That is clock gating. The goal of this technique is to disable or suppress propagation of transitions to some part of the clock path under certain condition. Power savings happen due to reduction in switching capacitance in the clock network, reduction in switching activity in the logic fed by the storage elements, since unnecessary transitions are not loaded when clock is not active. Since in a part of a circuit, clock is not reaching there, that's a sequential part obviously, that's why that part requires clock. So when clock is not reaching there, unnecessary transitions are not happening there. Transitions means leakage current, transitions means power consumption. So transitions are stopped there because that is not happening due to absence of clock. Overall power is saved. The clock signal is computed by function FCG. Here, clock is the system clock and clock G is the gated clock of the functional unit. This is the system clock, this is the logic, and what is output? That is gated clock. Clock gating is happening and gated clock is going to functional unit. Automatic clock gating is supported by modern EDA tools. They identify the circuits where clock gating can be inserted. EDA tools are equipped with this feature because it's a necessary feature. There are many clock gating styles implemented to optimize power in VLSI circuit: latch-free based design and latch-based design. This is a latch-based design and this is latch-free based design. It's an AND gate. Enable is here, clock is here. That is the gated clock. And that is enable is going inside, the clock is here, and this is gated clock. So it is latch-free, that is AND gate based or gate based, and that is latch-based design. This is deep clock. Not only gated clock, the latching property is used here. We will see it later in details. So we are done with this slide. We will move to the next slide. Clock gated versus non-clock gated resistors. There are 4 different configurations, circuit configuration. This one is non-clock gated resistor. Clock is directly going here in the resistor. This is gated enable clock. So clock gating, this gated clock signal is connected with this resistor. Here, these two are also non-clock gating circuit. One is without enable, another one is with enable. Enable is another input. Enable used to control it. So clock is directly going inside. There is input and output. There is no enable port. Here there is an enable pin and this is clock going. There is no clock gating. Direct clock is connected with the resistor. So these are different 4 configurations. Now we are done with this slide. Now let's move to the next slide and try to understand different types of clock gating. Now different types of clock gating. First, most of the commonly used clock gating techniques. There are 4: AND based, latch based, flip flop based, and mux based. Now there are some advanced clock gating also. Now there are some advanced clock gating schemes. Clock gating without enable signal and clock gating with enable signal. Now clock gating without enable signal, that is bus specific, threshold based clock gating, and optimized bus specific. And this clock gating with enable, local explicit clock gating, and enhanced clock gating. So these are the types of clock gating we will discuss here. So basic clock gating without enable signal, AND based, latch based, flip flop based, and mux based. First AND based and latch based. So this is AND based clock gating circuit. In AND gate based scheme, the enable signal explicitly control the clock input to the logic block. Here, if enable signal goes inactive between the clock pulse, clock output prematurely terminates. That's a hazard problem. Or if enable goes multiple times on and off between clock pulses, then it generates multiple clock pulses. This restriction makes this circuit inappropriate. So we know when both these pins are 1, then only we will get 1. Otherwise, for any other combination that is 0, 0, obviously will be 0, 0, 1, 0, 1, 0, 0. If that is the clock train, that is the input clock train, and we want a gated clock train here, as long as enable is 1, we will get the same clock train here. When enable is 0, there will not be any clock. Now, we want this clock trend to be replicate this one input here. Suddenly, for any reason, if enable become prematurely terminated, like become 0, that time we will not get the clock here. That will be 0. Otherwise, as long as this clock is 1, by that time, if enable for multiple times become 1 0 1 0 1 0, so that pattern will not replicated here. We will get multiple clock pulses here. So that is an erroneous situation. That is an issue with this configuration. Now latch-based clock gating. In latch-based clock gating, there is a level-sensitive latch that hold the enable value. When clock signal is going here, as long as this clock, it's level sensitive, as long as this clock is up, its enabling value is get latched by this latch. This latch holds that value. When it's 1, even within that period of time, the enable get down, it will not register that one. At the same time, if genuinely that value has to be down, that will also get registered when the next positive level will come, that time it will, because this latch is level sensitive. Hazard problem is not going to happen here, because as long as clock pulse is 1, when this clock pulse is at high level, whatever value enable pin was there, that is latched. So that value is here. So for that time period, it will stay at that value. So this is latch-based clock gating. We are done with this slide. We will move to the next slide. This is D flip-flop based clock gating. Instead of latch, there is a D flip-flop. A similar technique to latch-based design, with one difference that instead of latch, D flip-flop is used here. Area overhead increases much in comparison to latch-based technique. Here, area overhead is higher. Another, this clock gating circuit has a drawback that here also, if that is the clock trend, it's not uniform. It should be uniform. So, and suppose it's a positive, it's sensitive. So, whatever enable value is present, it gets reflected when the next positive edge is coming. If it's positive, if its enable is high, it will reflect here. At the same time, by that time, if the enable is genuinely gone down, till this next edge come, it will remain in the old state. That will not reflected here. It's edge sensitive. Only that positive edge will come and that will get reflected here. Now, marks-based clock gating. In this technique, the feedback path is controlled by the marks. Marks is controlled by select line when it is required to close or open the feedback path. This circuit is simply robust and often a reasonable choice, but this circuit uses one fairly expensive marks per bit and consume more power. It's consume more power and expense to implement this circuit is more. So it's expensive. And marks select, that one is with this select pin, that feedback path is controlled. So we are done with this 4 configuration. Now let's take a look at the advanced clock gating. Bus specific, threshold based clock gating and optimized bus specific clock. Bus specific clock gating. So bus specific clock gating is used to reduce the dynamic power, and it can be realized using D flip-flops and XOR and OR gates. This is the circuit configuration: XOR gate, OR gate, AND gate, and D flip-flop. Bus specific clock gating circuit compares the input and outputs and gets the clock when they are equal. D flip-flop, whatever is in its input, that is transported to the output. So input, if input is 0, clock is there, output will be 0. Input is 1, clock is there, output will be 1. So when both input and output are same, that means data has been transferred from input to output. Now there is no transition, or there is no data is waiting. So clock was there, data has been transferred from input to output. Now we can get the clock. So there will be no more transition. When new data will come, suppose initially it was 0, transition happened, data has been transferred to the output. Now we can get the clock. Clock should not reach here. Now suppose 1 has come here, and since clock is not applied, clock is gated, that data has not been transferred to output. Here is 1, here is 0. What will happen? 1 and 0 in the input of XOR gate. That means that will be 1. 1 will be here. When clock is 1, that 1 will pass here and the clock will activate. So when there is a change in the input data of gated flip-flops, then only the gated clock is applying for the flip-flop. Otherwise, the gated clock signal is not applying. Power consumption will be high if output toggle rate increases, which indicates high switching activity of the signal. So if that toggling rate or switching rate is very high, 1010, high frequency, whenever data is changing in very high frequency, every part of this circuit will be used, this big circuit here. So that circuit is getting used. So power consumption will increase. Now threshold-based clock gating is another data-driven clock gating technique which actually do some improvement in this power consumption issue of the bus-specific clock gating. In this technique, toggle rates of flip-flops of non-clock gating circuit need to be tested at first time, and then according to the list of toggle rate, those flip-flops are divided into two parts. In this way, disadvantages of bus-specific clock gating technique is removed. They are grouped and then clock gated. This is the bus-specific clock gating. Now we will move to the next slide. Now optimized bus-specific clock gating. This is a fine-grained and activity-driven clock methodology. The flip-flops are clustered based on relationship between them, and the problem of gated flip-flop selection is reduced from exponential complexity into linear. This configuration reduces the complexity. It was by comparing the inputs and output and gets the clock when they are equal. When there is any change, then only be here. Then only that part will get activated. Here it's OR gate is used. Even one signal is 1, even output is 1. So suppose here it's 1 is there, it's clock gated already, equal 0. Initially it was 0, here it's 0. So data has already been transferred from input to output. There is no new data to get transferred. So clock signal, right now clock signal is not present. So it's basically clock gate. We understand that. Now new signal has come, new data, that is 1. At output it's 0. So 1, 0, that is fed to a XOR gate, 1 and 0. So that is 1, A B bar plus A bar B. So that is 1. Output of this one is 1. So that data will be here, and with up of the clock, when that is 1 also, 1 and 1. So clock will be activated here. Clock will be activated and that 1 will transfer to here. Again, when 1 and 1 both are transferred to here, again that clock is, because both are 1 and 1, output of XOR is 0, others are not changing. So that is here. We are done with this slide. We will move to the next slide. Now advanced clock gating with enable signal, local explicit clock gating and enhanced clock gating. Now let's see its local explicit clock gating. Here clock of flip-flop is gated explicitly by using enable signal. Enable signal is here. This enable signal increases the control of the circuit explicitly. Here, as long as enable is equal to 0, no clock is passed off the flip-flop. If it's 0, output will be 0. Whatever be 1 or 0 is it's an AND gate, so obviously it will be 0, clock is 0. When it's 1, data is transferred to here is 1, and with the 1 that is high value, the clock will be replicated here. As long as this 1 is here, this clock signal will be replicated like this. As long as enable is 0, no clock is passed off the flip-flop and hence no power consumption is there, but power consumption starts when enable is equal to high. And if enable equal to 1 period is significantly high, then overall power consumption increases due to additional circuitry. It's an additional circuitry. If that enable equal to 1, as long as enable equal to 1, the clock will pass here. So all these circuitry, extra circuitry is in action. So power is dissipated here, power consumption is on, circuits are working, power consumption is there, power dissipation is there. So whatever we can save using clock gating, that outweighs by this power consumption. This is local explicit clock gating. Next is enhanced clock gating. This method combines both bus-specific clock gating and local enhanced clock gating and make use of advantages of both the method. In BSCG, switching activity increases the power dissipation, which is eliminated by using enable signal, which gated the circuit for that much period of time. So here also it compares. XOR gate is present here, enable is there. As when we want, then only clock is applied. Otherwise, with enable, if we are just increasing, more controlling this circuit is controlled through enable. If the mentioned situation is not emerged, then this method consume more power because of complex circuit than previous methods. So this is a complex circuit, extra circuitry is there, this enable is here. It consumes power. When it's in action, it actually consumes a lot of power. This is enhanced clock gating. Now we will move to the next slide. It's a typical clock-gated circuit. Clock gating can reduce the power consumed by flip-flops and clock distribution network. A group of flip-flops are identified and clock port of each flip-flop connected with the output of clock gating circuit. There are 3 clusters of resistors or flip-flops, 3 clusters. This is the system clock going inside. In this cluster, enable from logic Y. Some logic is implemented here that is getting used as enable, and here enable from logic X. Some logic X is there, that is the clock gating logic. This is the enable. So a common enable signal is used to control the clock gating circuit. For this cluster of flip-flop, there is a common logic X. That is enable. And for this cluster, logic Y. Enable comes from logic Y. Therefore, if a group of flip-flops which share a common enable term have clock gating implemented, the flip-flop will consume 0 dynamic power as long as the enable term is false. So if enable term is false or enable is equal to 0, there is no clock signal. Clock signal is gated through using this enable logic. So if enable is 0, there will be no clock signal. There are 2 techniques to implement clock gating. One is type matching, another is delay matching. This is a general circuitry for typical clock gating circuit. Now we will see what are type and delay matching clock gating. In type matching clock gating, same logic gates are used in same levels. Here also, similar types of gates are used. And here in delay matching clock gating, cells with same timing requirements are used. These are not similar type. At this level, 2 different types of gates are used. Although they are used because of their timing requirement. In this level, similar type. That's why the name is type matching. And here it's delay matching. Delay or timing requirement is the matching factor here. So this is delay matching clock gating. And now, multiple stage clock gating. Multi-stage clock gating style exists where the clock gating is cascaded. The clock signal of the first stage clock gating, that is CG1 stage, is gated by the second stage clock gating, CG stage 2. The gated clock signal should arrive at CG1 stage earlier than the enable signals, enable 1, enable B and enable C, to maintain the functional correctness of the circuit. This is the stage 1, although this stage is gated by stage 2. This is first level of clock is going here, enable is there. If this enable is 0, this stage is not activated. So the clock signal of first stage clock gating is gated by the second stage clock gating. So this is first stage and this is second stage, and this stage controls this stage 1. Clock is going here, although enables are there. At that stage, enables are there, and the gated clock signal should arrive at CG stage 1 earlier than the enable signals. If stage 2 is completely activated, clock signal will come here, come to here, here and here. And that should come earlier compared to enable A, enable B, enable C. It's already present, enable will come and clock signal will go there. That is, if enable A, enable B and enable C depend on the outputs of other flip-flop in the circuit, the minimum delay of enable signals should be larger than the gated clock. And then when data will come here, this clock signal is reaching here. When data will come here, data will go outside. This is multiple stage clock gating. Now, advantages and challenges of clock gating. Dynamic power reduction. In the clock gating, a clock signal doesn't reach idle parts of the circuit. Power is saved as switching activity minimized. That we followed in clock gating. Reduced heat generation. Since switching is less, power consumption reduces. As a result, heat generation reduces. And enhanced battery life. For battery-powered mobile devices, clock gating is very useful. Since power dissipation reduces, battery life increases. These all are movable devices, very popular nowadays. And now challenges. Timing violations. Introduction of gating logic may lead to setup and hold time violation. We have seen that in multi-stage clock gating slide, we have seen that in stage 1, clock must reach first and then enable will come. So that timing violation may happen. That's a crucial factor in case of clock gating. And now synchronization issue. There are multiple parts and we have a constraint of power. So some part clock signal will be there, some part will work there at certain point of time, then another part. This synchronization should be taken care well of, otherwise there will be mismatch might occur. Since the clock is enabled and disabled in various parts, that might lead to synchronization problem and delay before gated clock. There are extra logics are there, so a delay get introduced there. Clock path increases, delay get introduced. So these are advantages and challenges of clock gating. We are done with this slide and we are done with today's discussion that we had for clock gating. Now let's take a look at the pointers we are going to discuss in today's episode. First, cell or gate or propagation delay, first slide, and then cell or gate or propagation delay, second slide. Third, clock delay or latency. Fourth, more on clock latency. Fifth, transition delay. Next, what is clock skew? Different types of clock skew. Next, what is jitter? Various types of jitter, path and net delay. And finally, input, output and exit delay. Now let's move to the first slide. First slide is on cell or gate or propagation delay. Recently, we have completed a series on interconnect. While discussing that, we have mentioned about two types of delays. One is propagation or cell delay, or another is interconnect delay. So actually, signal transmission in a circuit is not an instantaneous process. It takes some time. That finite time is called delay, and delay has mostly two different components. First is gate delay, another is net delay or wire delay. In last series we have discussed about interconnect or wire delay, and today we will discuss about different types of delay. On that, this is the first one, that is cell or gate or propagation delay. That is basically time required in transmission of signal through the gate. This is the time required in transmission of the signal. If this is the gate, signal will travel from here, this point, to that point, and that will take some finite time. That is the basically cell delay. Next, signal transmission is not instantaneous and there is a finite time gap between the signal applied at the input of the gate and response of the input found at output of the gate. That we have already mentioned, that signal transmission is not basically instantaneous and there is finite time gap between the signal applied at the input of the gate and response of that input found at the output of the gate. So although we are applying signal here or the switching in the input is happening here in time domain, it will reflect at the output pin after some time here. That is the difference. That is the time difference. That is the delay basically. And propagation delay for rising and falling edge are not same. So here at the input, this switching is from 0 to 1, that is a rising edge, and here it's 1 to 0, that is a falling edge. So obviously at the output, since it's a NOT gate, the response will be just opposite. Like when it at input it's 0 to 1, at output it will be 1 to 0, that is high to low, and that delay related to this high to low transition at the output is called TPHL, that is high to low delay, and in a similar manner it's called TPLH, and these two are not same. The propagation delay TP is defined as the average of TPLH and TPHL, and TP is equal to TPLH plus TPHL. So if that is the total waveform, total delay is basically summation of these two. So we are done with this slide. Now let's move to the next slide. Again, cell or gate or propagation delay. TPLH, that is response time of gate for low to high output transition while input switching from high to low. That is, input is switching from high to low, and that time output is transiting from low to high. That delay is called TPLH. Another one is TPHL, response time of gate for a high to low output transition while input switching from low to high. Input is switching from low to high and the output is from high to low. The delay is usually calculated at 50% point of input-output switching. Ideally, we assume the signal is rising just like that, a straight line. That means in time domain, it's instantaneous. There is no time delay. From 0 to 1, this transition happen ideally if we take the waveform like that. Actually, it doesn't happen. It takes some finite time to reach its peak value. So when we calculate the delay, we always try to do it 50%. If that is the peak value and that is the minimum value, so in between that, just exactly between that is called 50%. And here also, while it was high and it's going down, so minimum, just 50% of minimum to maximum, that's transition. So 50% to 50%. Here it's 50% of that output signal. So, and here is the 50% of the input signal. So that the difference between these two 50% is TPHL. Similarly, TPLH. The delay is usually calculated at 50% of input output switching. Rise time. Time it takes for leading edge of a pulse to rise from its minimum to maximum value. Rise time is typically measured from 10% to 9% of the value. So TR. This is the rising time it takes for the leading edge of a pulse to rise from its minimum to maximum value. Rise time is typically measured from 10% to 90% of the value. This is the rise time. This is the 10% of, this is 10%, it is 90%. This is in between time, how much it takes to rise from 10% of the value to 90% of the value or magnitude. It's called rising time. Similarly, fall time it takes for falling edge of a pulse to fall from its maximum to its minimum value. Fall time is typically measured from 10% to 90% of the value. So we are done with this slide. Now let's move to the next slide. Now clock delay or latency. Clock latency or clock insertion delay. So clock delay, clock latency, clock insertion delay all point to the same thing. Defined as the amount of time taken by the clock signal in traveling from its source to the sink. In a system, there are flip-flops or time-dependent or sequential components. To operate sequential components properly, we need clock signal. So clock signal is also another signal. In real world, it takes some time to travel from one point to another. Clock-dependent or clock-driven flip-flops, they are called sync. If that is the clock source, obviously it will get connected with some flip-flop, and these are the flip-flops. So basically this is the path the signal, clock signal would traverse from clock source to flip-flop A, and that is the path for flip-flop B. So this is the clock latency. This the time it requires to cover this finite path is the clock latency or clock insertion delay, defined as the amount of time taken by the clock signal in traveling from its source to the sinks. Next, clock latency comprises of two components. One is clock source latency, another is clock network latency. Now let's see what are those two things. Clock latency is basically summation of source latency and network latency. Clock source latency or source insertion delay is defined as the time taken by the clock signal to reach the clock definition point from clock source. If that is the clock source like PLL oscillator or some other source from external clock source, when the signal is entering the design, there is a point where it's defined as the clock definition point. This is the clock definition point, but this is not the origin of the clock. Origin of the clock signal is clock source. So from clock source to this definition point, it's a finite distance and the signal takes finite time to travel. That is source latency, clock source latency. And from there, within this network, the signal takes some time to travel. That is network latency. This clock source latency also known as source insertion delay, and clock network latency or network insertion delay is defined as the time taken by the clock signal in traversing from clock definition point to the sink. Clock definition point to the sink is network latency, and from clock source to clock definition point is source latency. We are done with this slide. Now let's move to the next slide. More on clock latency. Now this is another diagram where the same thing is repeated for generated clock. So a generated clock, this is a system with generated clock. A generated clock is derived from master clock. A master clock is a clock defined using the create clock specification, and when a new clock is generated in a design that is based on master clock, the new clock can be defined as generated clock. That is the master clock. If the generated clock is going inside the network or the circuit or the design, so that is the point we have defined as the clock definition point. So from clock source to clock divider is used to generate this generated clock. So from clock source to definition point is basically source latency, and from there to the sync path, that is network latency. Pre-CTS latency and post-CTS latency, that is also defined in VLSI. Latency is the summation of source latency and network latency, as we have said. Now pre-CTS estimated latency is considered, because pre-CTS we consider the estimated latency and during the synthesis, and after that propagated latency is considered. So we are done with this slide. Now let's move to the next slide. Transition delay. This is the diagram, defined as the time taken to change the state of the signal. That is, this is the minimum value, this is the maximum value. In digital we say this is a 0 and this is 1. So the 0 to 1 transition, it's taking some time, that finite time. Again from 1 to 0 also it's taking some time, that is transition time for a signal. Time taken for transition from logic 0 to 1 or 1 to 0, expressed as rate of change of logic or the speed of transition, how fast it's changing its logic state, that is rate of change of the logic or the speed of the transition. Also termed as Skew and measured in volt per nanosecond. Rise time is defined as the time taken for signal to reach from low threshold voltage to high threshold voltage. Fall time is defined as the time taken for a signal to reach from high threshold voltage to low threshold voltage. Fall time is defined as the time taken for a signal to reach from high threshold voltage to low threshold. And both rise and fall time measured in absolute value or percent. Low and high thresholds are fixed voltage levels around the mid volt. So that is the mid value, that is 50%, and low and high threshold voltage are measured around this. Threshold voltages can either be 10% and 90% respectively, or 20% and 80%. These are two commonly used convention of measuring low and high threshold voltage. Either it's 10% is the low and 90% is the higher threshold, or 20% is the lower threshold and 80% is the higher threshold. The percent levels are converted to absolute voltage levels at time of measurement by calculating percentage from difference between starting voltage level and final settled voltage level. First we express it in percentage, and while doing the calculation, what we do with respect to V minimum and V maximum, we measure or we express these threshold voltages. We are done with this slide. Now let's move to the next slide. Now clock skew. Clock skew is defined as the difference of insertion delays of two flops belonging to the same clock domain. Every component adds some delay in signal transition. Clock signal take finite time to travel from one point to another, so there is time difference between arrival of clock signal to two different flip-flops. Difference between arrival of clock of two flip-flops is skew. There are two types of skew, local skew and global skew. If this is the clock, common clock, and then it's getting divided. Here it's for flip-flop 1, then flip-flop 2, and then flip-flop 3. So signal doesn't reach all these flip-flop at the same time, although they belong to the same clock domain. So there is a difference in time because it's a signal and a real signal is traveling through a real system. So it will take some time. So clock skew is defined as the difference of insertion delays of two flops. Insertion delay means the time taken in clock signal to travel from clock source to the sync point. So that's a first sync point, it's another sync point, it's another sync point. From definition point, that flip-flop 1, the network delay due to network latency basically is different. Network latency for this one is different, for this one is different. So the skew, the delay or the skew became different for all the flip-flop. And skew value can be positive or negative. So here we are showing positive skews only, not negative. So there are two types of skew value, positive skew value and negative skew value. So let's see what are they. We are done with this slide, and now let's move to the next slide. So different types of clock skew. Two types of skew depending on position of clock. One is local skew, another is global skew. This is the diagram. This is the clock. Now the clock signal is getting divided in two parts here. This is flip-flop 1, then combinational circuit, then flip-flop 2, then flip-flop 3. Here also some other flip-flops. So this is the shortest path. As we can see, signal will travel from this clock to finally reach here, and when signal is coming in this point and this point, there is a finite difference, that is local skew, FF2 minus FF1. Similarly, FF3 minus FF2, FF4 minus FF3, these are local. Now this is the longest clock path. And here also in this segment also there are local skews. And when we consider the global skew, that is longest clock path minus shortest clock path, the time taken in reaching the clock signal from here to here and from here to here, that is the global skew. So local skew is the difference of insertion delays of two communicating flops of same clock domain. Two communicating flops in the same clock domain, local skew is defined as the difference of insertion delays between two communicating flops in the same clock domain. Global skew is the difference between the delay times for earliest clock reaching the flip-flop and latest clock reaching the flip-flop for a same clock domain. Now positive and negative. If the capture flop receives clock signal later than the launch flop, then it results in positive. This is the launch flop, this is the capture flop. It's receiving the clock signal later. So this is positive skew basically. And if the launch flip-flop receives clock signal late than the capture flop, then all negative. This is the launch flip-flop, the capture flip-flop. The launch flip-flop is basically getting the clock signal late. So the capture flip-flop is getting the clock signal earlier, that is negative skew. So we know now there are 4 different types of clock skew. One is local skew, another one is global skew, and another 2 are positive and negative skew. So we are done with this slide. Now jitter. Jitter is another type of delay. Clock jitter is defined as the deviation of clock edge from its ideal position in time. It's like uncertainty. This is the ideal clock edge should be like that and might deviate from its position in both sides in time axis. That is the jitter. Clock jitter is uncertainty in the clock edge. When this clock edge will come or the position, clock jitter is basically the uncertainty in the clock edge, as we can see. The cause may be noise, a fluctuating power source, or interference from nearby circuit. There could be many reasons. Jitter is very much present in circuits. Now, jitter can occur in both directions, positive and negative. In both directions, we can see that uncertainty is in both directions. This clock edge might come earlier, this clock edge might come later. So, in both the directions. Can be modeled by adding uncertainty regions around the rising and falling edges of the clock waveform. Clock jitter can be cycle to cycle, period jitter and long-term jitter. There are different types of jitter also. So one is cycle to cycle jitter, another is period jitter, another is long-term jitter. These are common jitters. So we are done with this slide and now let's move to the next slide. Now let's know about various jitter. Now, cycle to cycle jitter signifies the change in clock period across 2 consecutive cycles. This is a clock signal. So, a complete cycle, it's 15 nanosecond and another clock cycle is like that, it's 18 nanosecond. So, any 2 consecutive cycles like T2 and T1 are successive clock periods, then cycle to cycle jitter would be T2 minus T1. And now, period jitter is difference between ideal clock period and actual clock period measured with respect to ideal clock period. So, if the ideal clock period is 15 nanoseconds. So for this clock period, jitter is 0. We consider T0 as ideal and that is 15. So actually there is no jitter in this clock period. Although here there is a jitter, so it will be 3 nanoseconds. Right, T1 minus T0 because this is the ideal and period jitter is measured with respect to ideal clock period. So ideal clock period is 15 and T1 is 15. So there is no jitter. Ideal clock period is 15. T2 is 18. So there is a jitter of 3 nanoseconds. This is the calculation. Now long-term jitter. Long-term jitter is the deviation of clock edge from its ideal position for a clock with period 20 nanosecond. Ideally clock edges should arrive at 20 nanosecond, 40 nanosecond, 60 nanosecond, etc. If nth edge comes other than 20 into n nanosecond, there is long-term jitter for nth edge and that is equal to 20 multiplied by n minus 200. And half period jitter is the measure of maximum change in clock's output transition from its ideal position during 1/2 of period. It's calculated for half of the period, not the total period. We are done with this slide. Now let's move to the next slide. Now path and net delay. Path delay. Delay assigned to paths from each input to each output. The minimum time required for a signal from an input pin to propagate through combinational logic and appear at the external output pin, also known as pin-to-pin delay. The time taken in signal traveling to this path, that is the delay. It's a combinational logic and no clock is involved here. So that time, how long it takes for signal to travel from this input to output, that is measured as pin-to-pin delay or path delay. Now, net or wait delay. This net or wait delay is basically interconnect delay. We have already discussed in a series. The difference between time a signal is first applied to the net and the time it reaches to other devices connected to that net. That is basically a net delay or wait delay. It is due to the finite resistance, capacitance and inductance of the net. Instead of our devices, because of its size, inductance effect is also there. So we try to represent this net as a combination of resistance, inductance and capacitance, and these are basically parasitics of the wire, we know, and many delay models are there to calculate this delay. We have already discussed those delay models and done their calculations in previous series. So this is basically the net delay or wait delay. We already know. We are done with this slide. Now let's move to the next slide. Input, output and exit delay. Input delay is the time at which the data arrives at the input pin of the block from external circuit with respect to the reference clock. So from outside world, this is the system. This is the input pin from where it's going to within that system. So the time required from that external point to this point, this is the arrival time of the signal, that is the input delay. Next is output delay. Output delay is the time required by the external circuit before which the data has to arrive at the output pin of the block with respect to reference clock. From this system, the signal, it's leaving from this point and going this output point. This is the output time or output delay. That time required go to that point. This is the basically output delay. And exit delay is, it is defined as the delay in the longest path or the critical path between clock pad input and an output. It determines the maximum operating frequency of the design. This is the longest path, and the delay in that longest path or the critical path is basically exit delay. So three delays: input delay, output delay and exit delay. So we are done with this slide. And actually we are done with this episode, so we will conclude here.
Hey guys, welcome to the second episode of Static Timing Analysis in VLSI. In last episode, we have seen how STA works so fast with respect to the dynamic timing analysis. In this episode, we will broadly focus on the input-output of STA and the timing calculation of the STA engine. So today's menu is STA in the design flow in ASIC or SOC, STA engine input-output at a glance, STA output terminologies, timing expectation versus reality check, what is a timing analysis path, types of path under STA scanner, directed acyclic graph DAG concept and example, maximum and minimum path concept. So without any further delay, let's begin. STA is used only in digital design. There could be pre-layout STA, but the most significant is the post-layout STA. With the help of a flowchart, we will understand the position of STA in the chip design flow. First, we have our design specification, and in this direction the flow will go. Next, we do the RTL coding as per the design specification. Next, we do the verification of the RTL code that we have written. Next goes the synthesis, then the floor planning. Next, power routing. Here we enter in the backend part in the floor planning and power routing stage. Then comes the global placement. Next comes the detailed placement. Next to it comes the clock tree synthesis. Now our flowchart will move on the right hand side with the arrow, and the next step is global and detailed routing. The flowchart will now move upwards. Layout generation or changes. Next comes the DRC and the LVS. At next stage, once the layout is done, we do the parasitic extraction for a DRC and LVS clean layout. Next, when our parasitic extraction is ready, we do the static timing analysis. And do remember guys, this is the backend or post layout static timing analysis.
Now at this stage, if we find a violation, then we go back to the place and route stage. If we do not have a violation, then the design is ready for tape out. So from this chart, you can see that static timing analysis appears at a very crucial level, and this is very much important for the tape out. So many times you will see that in many of the books or online literature, this is called as a sign-off process. So sign-off means the design by the designer and the verification team, they are signing it off for the tape out process. So that's why the static timing analysis is a sign-off process. We are done with this particular slide. So let's move on. STA engine input output at a glance. In this slide, we will get familiar with all the inputs and outputs of static timing analysis engine. These are very important for your knowledge base. Here we have infographics for you. This is the static timing engine, and you can see its direction goes shorter in the below direction. So above it will be all the inputs and below it will be all the outputs. Our first input is synthesis tech library. So guys, basically this comes from the Foundry and inside the PDK, and this tech library has all the Foundry definition of the gates. Next input is gate level netlist. This is designed by the designer team who are designing it at the pre-layout level, that is in the RTL level. This is basically from the front end part. Next input is SDF. So it contains the delay, and it is also a file extension. So it contains all the designer defined delays. The next input file is design constraints in Tickle. Okay, it is also called a SDC file, and here we give all the timing constraints for the STA engine. Next, we have all the pre-characterized data for all the logic gates in the standard cell library. This is the timing model library, also called the .lib or the liberty file. So in this, all the pre-characterized data for the entire set of standard cells are there. Next, we have the output. The first output is AT or RAT. AT means arrival time, RAT means required arrival time. We'll see some slides later about this AT and RAT with detail. Next output is report or histogram. So STA engine do a huge amount of text reporting. Also, it gives us the histogram. So we will come what all the types of outputs in this report later on. The last one you can say is the design data. Now this design data comes through the Tickle interface, and in case you have not seen the first episode of Tickle in this channel, the link is given in the description, so you can go there and see the episode. I have explained there with vivid detail how this type of design data is processed through the STA engine APIs. So here we have the entire picture of what are the state of inputs and what are the outputs of a STA engine. We are done with this particular slide, so let's move on. STA outputs in detail. We have just seen all the input and output of STA. Now we will discuss about all the types of timing violation that comes in the output report of STA engine. So these are register to register delays, setup time check of all external synchronous inputs, hold time check of synchronous outputs, clock to queue, that is clock to output delay, pin to pin combinational delay, different analysis modes such as best, worst, typical, on chip variation, that is OCV. The list has not exhausted yet. To continue, here we go. Data to data checks, case analysis, multiple clocks per register, minimum pulse width checks, derived clocks, clock gating checks, netlist editing, report clock timing, clock reconvergence pessimism, worst arrival slew propagation, path based analysis, debugging delay calculation, and many more. So we are done with this particular slide, and this is a kind of exhaustive list what all things we can expect in our text output of the STA engine. So let's move on to the next slide. Timing expectation versus reality check. What we mean? We will discuss about the expectation versus reality check process for STA delay estimation versus verification. The designer designs a circuit keeping some predefined delays as estimation so that the design operate at desired gigahertz speed. In STA, we use a method called directed acyclic graph to serve this purpose. Let us see how. So we have estimated delay by a designer that we are just picking, and we have to compare it with the calculated delay, that is the actual delay coming from the STA engine. To do this, we have to superimpose the two things by some method. This is called directed acyclic graph. Now, this directed acyclic graph is a timing path or a set of timing paths. So this graph is realized on the timing path. We will see how. So this is the concept here. We are done with this particular slide. Timing analysis path. Path means reaching from one point to another point to next by going through logic gates, flip-flop, etc. But there is a catch. Not all such paths are called timing paths. So let us see which paths are called timing paths among all the paths in a design. So here we have a picture of our timing path, and in this picture we start from the left. Our path starts from a clock, goes through a flip-flop which is yellow color. Let me bring my mouse. So here starts from the clock, it goes through a flip-flop, then it crosses the AND gate, then a OR gate, then a MUX, then a XOR gate, and ends up in the data pin of another flip-flop. Any path subject to the timing analysis which start at a source of the clock ends at the D pin or data pin of a flip-flop. This is called typical timing path. So we are done with this particular slide. Let's move on. Types of path under STA scanner. We have a clear concept of timing path now. We move forward in this slide to get familiarized with 4 types of timing paths that a STA engine considers during its analysis. Here goes our graphics of a chip. Now let me one by one define the 4 types of timing path. First, input to register. You can see the label in the right hand side graphics of the chip. Next is register to register path. Also the label comes up on the right hand side. Next comes the register to the output path. The label is also shown there. And the 4th one is input to output. These are the 4 types of paths. So here, let me do a clear demarcation. From here to here is 1. From here to here is 2. From here to here is 3. And from here to here is 4. For rest of our STA series, we will deal with timing violation of these 4 types of timing paths. Remember it. Now, if you focus here, each path has a start point, an end point. There will be a calculated value of the delay. So guys, we'll see in further slides the actual example of such path. We are done with this particular slide, so let's move on. What is directed acyclic graph? As of now, we are familiar with the timing paths. Now let us superimpose the directed acyclic graph on it. We will use the below graphics for this purpose. So here our graphics is come on the screen. This graphic shows 2 starting point at the extreme left, this, and one end point at the extreme right. So this is that point. In between we have multiple logic gates connected as per the design. Here the gates are treated as nodes and nets. These are nets. This is a net. This is a net. This is a net. Nets are treated as links of the graph. So basically when we draw a graph, we constitute a graph with nodes and links. The nodes are here the gate and the links are here the net for this directed acyclic graph. So let me bring up this text. Netlist is represented in form of directed acyclic graph, also known as DAG or DAG. Delay values are associated with nodes, cells and links. That is, nodes are cells and links are nets, as I have shown in the graph. Total path delay is the sum of the path delay values. We'll see in an example. First, all the possible topological paths are extracted. Next, for each path, calculates its delay and compare it with the endpoints values, that is the required values. So this is how our comparing is done. So we are done with this slide. Let's move on to the next slide. Directed acyclic graph example. Let us now take one example to understand the directed acyclic graph. Here goes our graphics, and before that we have AT, which is arrival time, and RAT is required arrival time. These are abbreviation. I give the full expression of them here. Here goes our graphics. This is same as before, but we will add delay to each element now. Let me bring up the delays. So before delay, AT is equal to 2. Here AT is equal to 5. These are the arrival time delays. Here we have two inputs. One has 3, another has 1. For this one, we also have two inputs. They have 2 and 1. Here we have 3 and 1 for the two inputs. And then in the final gate, we have 3 and 2 for the two input nodes. Now we define RAT, that is required arrival time, is equal to 10. So now let us calculate the total values. This is how we calculate. 2 plus 2 plus 3 equal to 7. So here is the first one. 2 plus 2 plus 3 is equal to 7. So this is okay because here it is within the RAT range. Okay, what we have specified as RAT, it is within that specific range. The next one we bring up is 2 plus 3 plus 1 plus 3 equal to 9. So 2 plus 3 plus 1 plus 3 is equal to 9. So this is again within the required arrival time. So it is okay. This path is okay. Next we have 2 plus 3 plus 3 plus 2. 2 plus 3 plus 3 plus 2. So this is equal to 10, and this is also okay because it meets the RAT. The next one is 5 plus 1 plus 1 plus 3. Now here 5 plus 1 plus 1 plus 3. This path is not okay. The next one is 5 plus 1 plus 2 is equal to 8, and this path is okay. So here we have shown the example of a directed acyclic graph, and we have seen how the calculations are done on this graph for the AT or the delays that have been defined and the versus the RAT. So we do the AT versus RAT comparison, and we point out the path which has problem, that is which is not okay for the timing. So we are done with this particular slide and the example. Let's move on. Maximum and minimum path concept. So far we are clear enough with timing path, its representation as directed acyclic graph. Now we will get familiar with the concept of max path and min path. We will take the help of these graphics for our understanding. So I have bring up the graphics. Here you can see from the left what we have. Here we have a flip-flop, then here we have a OR gate, here we have a NAND gate, here we have a NAND, we have a NOT, here we have a OR, here we have a XOR gate, here we have a flip-flop. So here in the graphics we can see that it is highlighted as the minimum path, and here it is the maximum path. Now let me bring up the text. A max path is not the physical maximum length path. So physical length means how much long the path is. It is not like that. It is with respect to the delay. So here it is the maximum path. In red we have written this. This is the maximum path. A minimum path is the path with the smallest delay. So here we can see the minimum path. So here, since in this path most number of gates are there, so it considered as a maximum path, and here we have the least number of gates and the delay, we call this a minimum path. So guys, we are done with this particular slide. Welcome to the 4th episode of STA. In previous episode, we have talked about various delays. In this episode, we will talk about multiple timing concept, which will help you to understand, debug, and root cause analysis in the STA report analysis. So today's menu is, first we talk about clock latency and skew, then setup and hold time concept, setup constraints from timing.lib. Next, we cover hold constraints from timing.lib. We talk about setup equation concept. We talk about hold equation concept. We talk about multi-cycle path concept. And finally, we talk about half cycle path concept. So this is the menu for today. Without any further delay, let's begin. Clock latency and skew. When we work with any STA engine, we need to provide some initial constraint to be used during the STA engine run. Clock latency is such a factor which we need to initialize. Often the clock skew concept is entangled with the clock latency to strike out the difference between the two. Hence, we will talk about both side by side in this particular slide. Here comes our graphics. Now, let me bring up the mouse to describe the graphics. Here, it is our clock source. Here, clock tree is there. Generally, this is done at the clock tree synthesis stage. Now, you can see these are buffers. I have colored them to just for the distinctiveness. And here you can see there are the 3 different flip-flops, 1, 2, and 3. These are also colored in different colors to become very much distinctive. Now, let me bring up the text. Clock latency is the clock traversing time between source and endpoint. The latency in STA engine can be fine-tuned for the clock source various conditioning such as rise, fall, min, max, and early or late. So for all these conditions, the latency can be fine-tuned for the clock source. Now, if you see in this picture, here the clock starts and it reaches through the different branches to different flip-flops, and our clock latency is measured from the clock till the same point of each of these branches. So this is the clock latency. So this is basically the time that the clock takes to traverse from its source point to any of the branch. Clock skew is the difference in arrival time in between two endpoints of the clock tree. It is the outcome of the clock tree synthesis. This is how we define it. In actual practice, in the STA tools, we define the clock latency with this particular command. Now, all the text are there. Let me again point to the clock skew. So, the clock skew is the difference in arrival time in different branches. So, from branch 1 to branch 2, from branch 2 to branch 3, or we can calculate from branch 1 to branch 3. So, if there are many more branches, so we can calculate in between any of the two branches the difference in the arrival time. Because here it is very simplistic figure, but when we actually deal with a circuit which has millions of gates, this clock tree branching will not be very much simple, and there could be clock gating also. This is the definition and simplistic figure just to keep a snapshot in your mind. So this is clock latency and these are the clock skew. So we are done with this particular slide. So let's move on. Setup and hold time concept. The setup and hold time is the key factor in STA. These two can be found in violation report of STA engine output. So you must have the concept to debug and root cause analysis. So let me bring up the infographics for the concept. As you can see, the graphics contain two flip-flops. These are called launch flip-flop and capture flip-flop. So I have distinctly colored them. The launch flip-flop is green and the capture one is pink. In between these two, there is a blue colored symbol, which is basically a symbol of a cloud. This represents the combinational circuitry through which the data traverses from launch flip-flop to capture flip-flop. Below, there is a timing diagram to visualize the data and clock transition side by side. So this diagram, we have clock here and we have the data transition. And if you look carefully, we have placed the hold and the setup markers here for this hold and setup time nearest to the respective flip-flop in the definition. Setup time. This is the cushioning time for which the data must be stable before a capture clock transition happens in the capture flip-flop. Now guys, let me bring the mouse pointer here we are talking about the setup time. You can see the capture flip-flop must get a time cushion as I am pointing with my mouse before the capture edge of the clock hits the capture flip-flop. This is the capture edge at the capture flip-flop. So this cushioning time lets the capture flip-flop to set it up for the capture of the arrived data. So data, you can see data is arriving through this path, and this particular capture flip-flop will make itself ready to receive the data. Hence, we call it the setup time. That means the capture flip-flop is setting itself up for the data. So hence, this particular time cushion which we are providing is termed as setup time. Any change in the data inside the cushioning time termed as violation. So you can see the data variation is happening here and not inside this particular cushioning time. If this data transition, this data is getting transition here, if this happens within this time cushion, in actual circuit, the STA engine will catch it as a setup violation. Hold time, cushioning time for which the data must be stable after a launch clock transition happens in the launch flip-flop. So now let us come to the launch flip-flop, and we are talking about hold time here. So here you can see that this cushioning time, this particular cushioning time after the launch edge of the clock has arrived. So this means here this is the launch edge of the clock, and we are providing additional cushion here, which is the hold time, helps the data from flip-flop, this particular flip-flop means launch flip-flop, helps the data from the launch flip-flop to jump and run into the data bus properly. So this is basically the data bus. This time cushion for which we are holding the data stable helps the data to jump into the data bus and run stable. Thus, the data is held stable for the cushioning time for successful launch. After this cushioning time, we can see the data gets changed in the input data bus. This change is okay. The change in the data inside the cushioning area is flagged as the hold violation. So we can see that we are holding this data line stable for this particular time cushion, and the data jumps into the data bus properly, and after certain time, this much time, the data start to change, which is okay. But if this transition is happening within this particular cushioning time, here the STI engine will catch it as a hold violation. So we are done with this particular slide. Let's move on. Setup constraints from timing lib. In last slide, we have talked about the setup and hold time. In a design, there will be millions of logic gates, flip-flop, and other various standard cells. Now that for all these cells, where does the setup and hold constraints come from? How do STA engine gets all the data? In this and the next slide, we will discover. In this particular slide, we will talk about the setup constraints that a STA engine reads from the timing.lib file. So let me bring up the text. LU table template, setup template. The name is setup template and the dimension is 3 by 5. Variable 1, related pin transition. Variable 2, constrained pin transition. First index, that is index 1, which is corresponding to the variable 1, has 3 values. You can see 1, 2 and 3 values. Next comes the index 2, which is having 5 values. So you can see the 3 by 5 table, the row and columns will contain 3 versus 5 values as the row and column indexes. And we close it here. I'd like to emphasize here, this is a particular template that is a prototype. This arrives at the very early or the top of the .lib file. And when we have a definition of a particular standard cell, inside that we will have the exact table. So let me show it to you. Inside each cell, there will be a timing block, inside which there will be first the pin, which is a related pin, will be marked as related pin clock. Then timing type is setup falling. Rise constraint, setup template 3 by 5. Now you can see the actual table, the lookup table comes here. Here are the index values of the row index, that is P values 0.06, 0.3 and 0.6. Next is the index 2. It has 5 values 0.06, 0.18, 0.42, 0.6 and 1.2. So these three correspond to the three index values here and 5 index values are here. So let us have the table now. Values like that is this comes the first row, second row, third row, and we close it. Now you can see, let me bring my mouse pointer. 1, 2, 3. These values will be in the row 1, 2, 3, and 5 values 1, 2, 3, 4, 5. These will be column indexes. Now let me tell you that what this thing is all about. We can see the related pin transition and the constraint pin transition. So here generally we are talking about the related pin, right? So related pin is clock, and this table comes under a particular cell, and for a particular pin will be there. So that will be the constraint pin. Now we also have a similar table for the fall constraints. So we have a rise and fall constraints. Similarly here the three indexes for the rows are 0.06, 0.3 and 0.6, and there are 5 column indexes here. And next comes our table, first row, second row, third row, and we close the table. And we finally close the timing block. So this timing block will appear inside the .lib file deep down for each particular standard cell. Now you know that any particular standard cell means it could be a logic gate or it could be some other particular standard cell. So when the ST engine reads the .lib, it gathers all this data and it have a mapping of this timing will come for a particular pin of a particular cell and with respect to the pin clock. So if we say if this is for Q, right, the clock to Q transition. So clock to Q delay values, we will have the transition values. So we know that these are related pin transition, means these are clock transitions, and say if it is Q, so for Q transition. So we have the clock transitions here and we have the Q transitions here, and for each combination there could be one value coming. The ST engine will manage the calculation. How? Now if these indexes are exact values, then they will find the direct values. If some value is in between, so if there is a value between this and this and this and this, some value here and here, what the ST engine will do, it will use a numerical method called interpolation and find out the value. So here when this table is characterized during the Liberty file characterization, all the extreme values, so from here to here if we come diagonally, all the extreme values are covered in this table, so that we have all the extreme values. And as you know, any particular .lib is generated for various PVT conditions. So definitely for each PVT there will be a different .lib. Thus we get all the combination for all the kind of PVT variations. Now the STA engine have all these data inside, and when it dynamically calculates, right, the delay for different paths and all for the AT RAT factors that we have explained already in previous episodes, all these factors the STA engine judge from the data that reads from the .lib. So that is a very important factor to have all this data in the .lib, and this is how we are relating the setup and hold concept and the corresponding constraint that is coming from the .lib. This will be used in the actual STA engine when it runs, but whenever this run is happening, it will happen in a blink of an eye. We are done with this particular slide, so let's move on. Hold constraints. In this slide, we will explore the hold timing constraints from the timing.lib. Now here again, we have first the LU table template, and it is 3 by 5. So first variable is related pin transition. Variable 2 is a constraint pin transition. And here comes our the row index. And here comes our 5 column index, because the table is 3 by 5. As you can see here, 3 by 5. So 3 and 5 values are there. And here we close our table template. Again, I am mentioning this will be way up at the very beginning of the .lib, where you find all these templates. You can also have a similar word prototype of a table. Here we get the prototype for the row and column values. But in actual practice, for each cell, the actual data will come into the timing paragraph, you can say. So, or the timing block. And these hold constraints are like this. This is a one example. Related pin is clock. Timing type is hold falling. Rise constraint hold template 3 by 5. So this is rise constraint, and this will contain a 3 by 5 table. Row indexes are with, these are actual index values, and these actually overrides. So These three values are actually overriding these three values for that particular cell for which we are having this data. Next, we have 5 column values here, and we start the table. So first row, second row, and third row, and we have 5 corresponding columns. So our 3 values, 1, 2, 3, they sit here, 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 and these 5s will sit here, 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 here. So there will be 5 values. 1, 2, 3, 4, 5 here. Again, we close this particular rise constraint table, this lookup table, and next we have the fall constraint. Index 1, index 2, we have row and the column index values, and we have the first row, second row, third row, and we finally close it, and finally close the timing paragraph or the timing block. Here we have the hold constraints from the .lib. Again, I will say, so this will be for each and every standard cell, and they will be present in the .lib file, and for this reason you can see the .lib file will be very huge in text format. If you open up with editor like gvim or something, it will take some time to load, even though it's a text file. Another point is here, we both have rise and fall constraints. So means that for a rising or a falling condition, we have the both constraints. So because we don't know what is happening, so whether rise is happening or the fall is happening, so these are pre-characterized. And again, I am mentioning from going diagonally from here to here, all the possible values, all the extreme values are characterized, and any value coming in between the values will be found out by the numerical method called the interpolation, and the STA engine will do that with its intelligence. So this is all the whole constraints from the .lib file. We are done with this particular slide, so let's move on. Setup equation concept. In this slide, we will discuss about the setup equation. This is a must know for all of you. To realize the equation, we will take up help of the infographics. Let me bring it on the screen. Here. Now in this picture, there are 2 flip-flops. First one is the launch flip-flop colored in green, and the another is the capture flip-flop on the right hand side colored in pink. Now there is a blue cloud symbol used for the combinational path that the data passes through before reaching to the capture flip-flop. Our first path is from clock pin of the launch flip-flop to the D pin of the capture flip-flop. So this is our first path. This path is used for the data transmission. This path is used for the data transmission. The second path starts from the clock pin of the launch flip-flop and goes up to the clock pin of the capture flip-flop, passing through 2 buffers, buffer 1, buffer 2, or buffer 1, buffer 2. They have distinct colors. Now in this whole diagram, we can see there are several red dots here, 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 here. These red dots denotes the delay caused by their respective label. This dot has the label TCQ, this has the label TComp, this dot has the T setup, and this dot has T-Skew, and this dot is labeled with T. TCQ is the clock to queue delay for the internal elements in the launch flip-flop. This delay is caused by the circuitry inside the launch flip-flop in between the path of clock and queue. The next red dot is called as T-comp, which represent the delay of the blue colored combinational path. So here there could be any combinational path, and the wholesome delay of this combinational path is referred as T-comp. The next red dot is T setup, which is the time cushion at the data pin of the capture flip-flop. So here the data pin of this capture flip-flop is, this is the time cushion T setup. In the second path, T is the time period of the clock propagation, which has a red dot associated with it. The next dot is for the TQ, which is the skew due to the buffers around the red dots. Now, as per the definition of the setup time, the data should reach the D pin and stay stable. So for the cushioning time, the data must reach the D pin and stay stable, very much stable. To make this reality, the below equation must be satisfied. Now let me bring my mouse pointer here. So you can see TCQ plus TComp plus T setup. Now one thing here, the capture clock will come here, and all the delays are before that and we have the time cushion which is before that, so all are having the plus symbol, so this must be less than t plus t skew, and thus we can say the total time of traversing which is in the LHS must be less than or equal to the time of equation in the RHS of this equation. So the data in the path 1 must reach early than the clock propagation in path 2. So we are done with this particular slide. Hold equation concept. In this slide, we will discuss about hold equation. This is also a must know for you. We will take the help of an infographics to understand this equation. Let me bring the graphics. In this graphics, we have a launch flip-flop colored in green, a capture flip-flop colored in pink. We have multiple red dots along with their labels. These are either delay or the time cushion. The first from the left is TCQ, which is clock to queue transition delay. The next is T-hold, which is the time cushion for the hold time at the Q pin of the launch flip-flop. The next one is the T-comb, which is the delay due to the blue cloud representing a combinational path, and this T-comb the delay for this entire combinational path. The next one is the red dot in between two buffers. This represents the TQ. Now you can see that there are two paths in the infographic. Since this is for launching of the data, we do not involve the time period. Let me bring up the hold equation. In this equation, the minus sign is because T hold is the time cushion is appearing after the launch clock age has already appeared. In other words, this equation can also be rewritten as like this. So here done with the hold equation concept. So let's move on. Multi-cycle path concept. In this slide, we will get familiar with multi-cycle path concept. Now let me bring up the infographics for this. In this picture, there are two flip-flops. The data is traversing from the green one to the pink one. In between, we have a orange color cloud which represents some combinational circuits which contribute to delay. Now in the label you can see that the delay is a multiple of the time period t. Here it is 7 times of t. This could be any number. I mean the 7 instead of 7 it could be any number, but I would like to also emphasize these are real numbers and not imaginary number. So the path from the clock pin of flip-flop 1 to the data pin of flip-flop 2, this path is called a multi-cycle path. Let me bring up the definition. For a multi-cycle path, the combinational delay between the propagation from launch flip-flop to capture flip-flop is multiple of the clock time period. So this is the concept of the multi-cycle path, and we are done with this particular slide. So let's move on. Half cycle path. In this slide, we will get familiar with the half cycle path. This is not the same as the last slide, so don't jump into conclusion. Let me bring up the graphics to understand the concept. Now in this picture, the launch flip-flop, that is the green one, is negative age triggered as it can be observed by its symbol. Here we have the symbol. There is a bubble at the clock pin. On the other hand, the capture flip-flop, means this pink one, is positive age triggered flip-flop as it do not have a bubble at the clock pin. Now in the case of a square wave where on time is equal to off time, the data has to traverse in between these two flip-flops within a half cycle. This is because one rising edge followed by one falling edge at the beginning and middle of the entire time period. Undoubtedly, if we exchange the rising or falling edge for the beginning or middle of a square wave, the data traversing conditions remains the same. Let me bring up the definition now. A half cycle path lies between two positive and negative age triggered flip-flops. In the design, if there is such path where there are two flip-flops in between the data traversing is taking place, so one is positive age triggered and another one is negative age triggered, then that particular path of data transmission will be termed as half cycle path. So we are done with the concept and we're done with this slide. Hey guys, welcome to the third episode of static timing analysis. In last episodes, we have talked about the directed acyclic graph, which deals with the AT and RAT. In this episode, we will discuss about various delays which affect these AT RAT check in actual circuit. So here goes our menu for today. First, we talk about STA delays. Next, we will talk about propagation path delay. We will explore physical path delay. We will talk about pre-layout net delay calculation. We will talk about designer defined delay. We will talk about post-layout net delay. Next, we will talk about cell delay calculation. Next, we will discuss rise and fall slew concept and example from .lib file. So this is the menu for today. Let's begin without any further delay. STA delays. So let us get familiar with the delays in STA. In static timing analysis, STA, static delays such as gate delay and net delays are considered. In each path, these delays are compared against their required RAT, maximum and minimum values. The actual path delay is the sum of the net delay and the cell delay along with the timing path. Don't worry, we'll explore these things in subsequent slides. Net delay is the total time for charging or discharging all the parasitics. It is a function of parasitic R and C or coupling capacitor. Next, cell delay is the delay arc corresponding to the input and output ports of the cell. It is the function of slew, load, and process parameters. Wire load models, WLM, are fetched from the technology file. We are done with this particular slide, the introduction to the all STA delays and their different kinds. In subsequent slides, we will explore them one by one. Propagation path delay. In this slide, we will discuss graphically the basics of delay calculation. In any and every type of delay are defined or measured using this method at the bottom. Then they are put into some text format to feed the STA engine. So let me bring up the graphics. So here goes our graphics. This is input waveform, this is output waveform, and this is a 50% cut. This is the 50% cut. This is TF and this is TR. Here you can see that there are two waveforms. The above one is input waveform, which is generally called the reference waveform. The below one, which can be output of a logic gate or an IP or simply a design block. Whatever it is, the delay is measured on it. We can see in both the cases that there is a horizontal dotted line. See, this is the horizontal dotted line which cuts the waveform at 50% height. So if I consider this is the height from here to here, it cuts at the 50%. In both cases, it is the same. The y-axis, that means in this direction, is the voltage, and in the x direction, this is the x direction. X-axis is horizontal direction, is time. So we have voltage in this direction and time in this direction. So when we drop a perpendicular line from these cut points, say this is a cut point and we are dropping the line here in the x-axis, we get intersection points. So these are intersection points 1, 2, 3, 4. As I have mentioned earlier that the delay is calculated at the output waveform, hence this is called the fall time delay. So you can see here is the first cut and the second cut is dropped in the x-axis. We can measure it because due to the circuit operation, this waveform has just flipped vertically, and at the we are considering the 50% of this point and 50% of this point and dropping on the time axis so that we can measure the time shift. So this is called the fall time delay. And similarly, if we drop here at the x-axis and again here we drop, so here it is also got flipped, but from 50% to the 50% we are measuring here, and this is called the rise time delay. Now you may be wondering why we need both. In general, the slope of the rising and the falling edges are not same for a single waveform due to the design or the presence of the parasitic resistor, capacitor or coupling capacitor. So guys, here I have drawn the picture very much identical in real circuitry, these two slopes. So that means this slope and this slope will be different, and again this, when it passes through a block, this slope and this slope also will be different. So expect this thing in real cases. So we are done with this particular slide. So let's move on. Physical path delay. In this slide, we will zoom into the delay a bit further to understand from where physically it is coming from. Here is our total delay. It can be divided into two parts. One is the net delay. Net means the interconnects which connect all the logic gates in the circuit. And the cell delay. Cell delay means the logic gates. They have their intrinsic delays. The net delay is caused by the interconnecting net or metal or via routing at the layout level. It can be subdivided by the delay caused by the individual existence of a capacitor or coupling capacitor and a resistor or a resistor. That means both can be there. So P and R or C or R, all these combinations are possible for the net delay. The cell delay comes from the physical standard cells which have a circuit component as well as the metal 1 and metal 2 routing in each. So these cells are pre-characterized by the Liberty characterization tool to calculate input slew, output load, for various PVT corners. The cell delay varies from one type of the cell to another type of the cell. Also for the same cell, it varies when we change the cell height. As an example, I can say 60, 70, 90 and 12T. Here T means the metal track width. So when you deal with the standard cell, you come to know about the cell height, which is measured in terms of track. So these are different track and height. So even a single cell is there, it's all the delay values for it will be different for different track, and these cells are also packaged in different files. So the all possible permutation and combination of the cell height, process, temperature and operating voltage, etc. gives birth to a huge amount of data mining, which is captured into the .lib file for any standard cell library. So guys, I think we have talked enough on this slide. So let's move on to the next slide. Pre-layout net delay calculation. Before reaching to the layout, verification is done at the front end. Here, the designer needs to define the delay to check the AT versus RAT at even synthesis stage. The designer defined or hand calculated delay is called the wear load model. In this slide, we will talk about this. Wear load model. The net length is a function of the net fan out and chip area. So fan out, you know how many output it can drive, and the chip area is the physical area. For a given area, averages of R and C are estimated for different fan out. Then net delay is calculated simply as the product of R and C. So this is how the wear load model is generated. Now let us look into an example here. Let me bring my mouse pointer. Here I have given fan out in the first column, P value in the second column, R value in the third, and finally the product, that is the wear load model, is in the fourth column. So delay is equal to R multiplied by C. So if the fan out is 1, we have the C value is 0.015 and the R value comes as 0.012. Now the wear load model predicts the delay as 0.00018. If you multiply these two things, and you will get this result. Similarly, if the fan out is 2, the C value is 0.030, R value is 0.016. If you multiply them, this result, that is 0.00048, will come. So this is the delay in this case. The third case, here the fan out is 3. The C value is estimated as 0.046. The R value is here the 0.020. Now if we multiply these two, the outcome is 0.00092. So this is the wear load delay modeling. So I have given the theoretical as well as an example to understand the wear load model. So we are done with this particular slide. Let's move on. Designer defined delay. In last slide, we have talked about the wear load model. Now let us see how and where a designer can put these delays to feed them into the STA engine. So designer defined delay, here it can be fed into first the design constraint file. Second, in the SDF file, we have already talked about the all input outputs in STA, and there I have touch base these two files as the input. Here these two are text file, and the designer can include his defined delay into these two files. So manually these can be entered also. We will have a series coming up next after this particular STA series, which is currently going on, where we will deep dive into the technical details of these files formats used in STA analysis. So stay tuned, stay focused. We are done with this particular slide. Let's move on. Post layout, net delay, RC back annotation. So far we have talked about all the pre-layout delays. In this slide, we will enter into the junction point where the front end meets backend. Through infographics, we will explain how designer designed netlist catches the cough and cold of parasitic RC when its layout is realized. So here we go. This is our pre-layout circuit. When we realize the post layout circuit after the layout and we extract the SPF, DSPF, SPF, SBPF, etc., whatever you call, the post layout netlist comes as like this. Can you spot the difference? Yes, the difference is here and here. So these are the parasitic resistors that have been added. I have not complicated the structure with parasitic capacitors, but they will be still there. So it is just to exemplify you. So you can see that, let me bring my mouse pointer. In such circuits, what happens when there is a post layout netlist, the SPAF is created. These nodes, this is a node, this is a node, this is a node. So such nodes will generate multiple subnodes. These subnodes will be connected to the parasitic resistor, capacitor, and coupling capacitors, because these are metal routes in actual practice, and there will be the coupling capacitor will show the neighboring effect. So here I think the picture speaks for itself, and this picture also. In ST only, the PF or SBPF is used as these contain the information about nets only, as cell delay are picked up from .lib. So just for your information, I have dumped all the formats of the parasitic files, but in case of STA, PF or SBPF, SBPF is the binary format. It cannot be read by human. PF is the text file, so it can be read by any human being. So either SPF or SBPF is used in STA. So these are not used, but just for your knowledge purpose, I have put it there. So we are done with this particular slide. Let's move on. Cell delay calculation. PF is for the net, and for the cells, the design, we have the .lib that will contain the delays. Now the delay modeling inside the .lib file is done using these three different ways. Here goes our cell delay modeling, which is done through the .lib characterization, and there are three different delay models are there. NLDM. NLDM means nonlinear delay model. Here we use lookup table and interpolation method to find out the required delay. The next one is CCSM. CCSM means composite current source model. Here we use driver and receiver model to define the delays. The next one is ECSM, which means the effective current source model. This is the first and only open standard current source model which is well accepted in the industry. So we are done with this particular slide. So let's move on. Slew, rise and fall. In this particular slide, we will discuss about the most important element in STA, that is slew. We will take the help of an infographics to understand it properly. So here, this is our graphics. Now let me bring my mouse pointer. So here you can see the waveform is rising. Here it is flat, and then it is again decreasing. So I have intentionally kept the two inclination different, just to show you that in real life they may be different. And I have also exemplified the different kind of threshold, right? Here 10%, here 90%, here 20%, and 80%. So these kind of threshold, that is lower threshold, upper threshold. Again here it is upper threshold and lower threshold. So these type of various threshold values are kept in the industry and in different files as per the design, and many other factors are there controlling them. Now if we cut a waveform here at 10% and here at 90%, why we are cutting? The reason is that here this is not straight and then bends directly, because it is a capacitive action, so there will be a continuous bend, so we have to cut it somewhere. So just to get a flat inclination. Okay, this one. So this is called the rise slew. So here our threshold are 10% to 90%. Our rise slew is measured like that, and our fall slew, again here it will be capacitive action, and it will be a bending instead of a sharp bend. It will be a continuous bending, and to accommodate a direct slope here like this, we have to cut it at 80% and 20%. And here in the time axis we measure the fall slew like that. So this axis Y, it is voltage, and this axis, this is time. So here we measure the rise slew, and here we measure the fall slew. So although I have hard coded the 10 and 90% and 80 and 20%, it is not the thumb rule that this is for rise and this is for fall. So any combination can come out. So both can have 80-20 values here, both can have 10-90 and 10-90 here, and they can be different, or 80-20 in the rise slew or 10-90 in the fall slew. So there could be multiple combinations. So don't just have this only picture, but try to understand the concept where these slews are meant. In STA, the rising or falling waveforms are measured in terms of whether the transition is slow or fast. So this slew means that how much fast the transition is, that is from 0 to 1 or 1 to 0. The slew typically measured in terms of the transition time, that is the time it takes for a signal to transition between two specific levels, that is the 1 to 0 or 0 to 1. In the .lib file, the slew thresholds are defined in the particular fashion. Let us see an example. So falling edge threshold is defined as slew lower threshold PCT fall, that is then colon, then 20.0, and this line ends with the semicolon. Similarly, for slew upper threshold PCT fall, so this is fall slew. Let me bring my mouse pointer here. We are talking about fall slew, and this lower threshold is 20% and upper threshold is 80%. So here what we have depicted in the picture, the same thing you can read in text format in the .lib file. Now rising edge thresholds, slew lower threshold PCT rise. So here it is 10. So you can see here our threshold is, cut point is at 10%. Now slew upper threshold PCT rise is 90. So this is at the 90%. So this is the way of representation inside the .lib file, and this may, similar commands may be there within the STA tool also. So they may be exact or they may be a bit different, but this is the way of representation of the slew cut point. So we are done with this slide. Let's move on. Rise slew versus delay from the .lib. In this slide, we will exemplify the lookup table for rise slew versus delay in NLDM model of .lib. Here you can visualize the 2D lookup table LUT from which the STA engine picks up the delay. In case an exact value of the index is not found, then the STA engine does the interpolation technique to find it out. Here the computational intelligence of STA engine can be observed. So let me bring up the details. Here we are using the NLDM model, so I have highlighted. So first there will be a template. Template means this is the kind of prototype where we define the shorthand of the things. Variable 1 total output net capacitance. Variable 2 is the input net transition. So this is the first one is generally the row variable, and the second variable is the column variable. Now index 1, so this is a 5 by 5, so we have defined 5 indexes here, and index 2 we have defined 5 indexes there, and we close the template. So this template will be way up in the .lib file, and the next table, which is the actual table, that may come inside a particular cell. So this particular LU table template is common for all, but the actual template or the actual data for each cell will be different, and that will be in the inside each cell's definition inside the .lib. So let us see such example also. Rise transition, this will be definitely inside a cell. Then delay template 5 by 5, so we have a 5 by 5 table here. Index 1, now you can see that index 1 has again 5 values, but they are different from the initial values. So these are actual values of the cell. So these overrides the initial template values. Index 2, which is the column index, and index 1 is the row index, again has a 5 different values than the template values. So this overrides the template values whichever earlier was defined. Now we start the table. This is our first row. Here goes our second row. Each has 5 candidates. Third row, fourth row and fifth row, and here we close it. Let me bring my mouse pointer in to make you understand the things. So here our first row index is there, 5 values is there, 1 2 3 4 5. So they will sit just above here, 1 2 3 4 5. You can do an imagination, and the column values are the 1 2 3 4 5. So they will be here 1 2 3 4 5. So if we have to pick the value for this combination, this and this combination, that will be the first one. And similarly, we can move ahead and find a value. It's like you find a point in XY graph, right? You move to some X values, then you have some Y values like Cartesian coordinate, which has a X and Y kind of thing. So this is very similar. This table is very similar to that kind of interpretation. And now the question is, if there is a value lying in between here, so index 1, so we have actual case in actual simulation time, we have some values lying in between the first value and the second value, and there is another value which will be in between these and these values. So how to get that? The STI engine will use a numerical method called interpolation to find that value out, and it will find out. So these values are characterized keeping in mind that well extreme values, okay, so that it covers the entire spectrum. So there is an entire spectrum is covered here and entire spectrum covers here. So anything will come in between all these values. So if it is on the point, so this point and this point, the STI engine will find out the exact value, so this one. And if it is there some intermediate value, so it will do the interpolation. Now the things are very much clear that first the template is defined, it is way up in the .lib file, it is common for all the cells, but when we have a particular cell definition, we have this kind of table. So the name is common here, delay template 5x5, delay template 5x5, and the case is here the rise transition. So we are done with this particular example or slide, and let's move on. False slew versus delay from the .lib. In this slide, we will describe the 2D lookup table, that is LUT, of false slew versus delay from the .lib file. This will engrave the 2D LUT concept totally into your mind. Let me bring up the text. So again, I am highlighting that we are using NLDM model here, and here the template begins, LU table template, delay template 5x5. So we have 5 rows and 5 columns. Variable 1 is the row variable, that is total output net capacitance. Variable 2 is the column variable, is the input net transition. So here the first set of indexes, these are initial values, and again these are 5 set of index values for index 2. And now just again I emphasize here, variable 1, the value variation is index 1, and for variable 2 the value variation is index 2 variation. Now we close the template here. In actual cell we will find the fault transition table, that is 2D LUT, which will be like that. The name is common, the delay template 5x5, and the name is fault transition. And here we will see that index 1 has its actual or local values, which is for that particular cell, and this will override whatever we have defined in that table template. Now again here we have the second index, that is column index, and here we also have 5 values, and here we start table. Here goes our first row, second row, third row, fourth row, and fifth row, and we close the entire block. So here again these values will sit here, 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 and here, and these values will sit here, 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 and here. So this is a kind of table that helps you to get the delay values, not you actually, the STI engine. The STI engine will calculate the delay values either from the fixed point values for the XY coordinate kind of stuff. It will find the exact value. If it doesn't find the exact value, it will do the interpolation. So guys, I think we are done example here, and now the 2D LUT concept has engraved into your mind. Now you know how STI engine picks up the cell delay values. So we are done with this slide. Let's move on. Hey guys, welcome to the 7th episode of Static Timing Analysis. In today's episode, we will discuss about the design constraint file. This is a very important file because here we define the AT and RAT, which we have discussed in episode 1. Constraints are first defined in the synthesis stage, then they are reused in the pre-layout and post-layout SEA. The constraints make a realistic periphery of the ideal netlist. Let me introduce the constraints to you to today's menu. First, we talk about why we write constraints. Then, design constraint file introduction will be there. Frequently used design constraint commands will be introduced to you. We will recall the directed acyclic graph concept, arrival time, input delay, required arrival time, output delay. Everything is in terms of the constraints. Rise or fall slew design constraint. So this is the menu for today. So without any further delay, let's begin. Why we write constraints? Theoretically, I have already explained that the constraints make a realistic boundary to the ideal netlist during the simulation. We do this in bits and pieces. Let me walk you through such cases as an introduction. By default, in your design, the signal arrives at the input port at time equal to 0. In realistic cases, input signals arrive with a delay added to it. We can do such case by set input delay. We give a value here 2.5. Then we mention for which clock, that is dash clock, CLK, and for all inputs. The overall delay will be 2 nanoseconds relative to the system clock. Thus, you can see first your system was very much ideal. Then we have given this command with a particular delay value to the input, and that makes the system perform like a real case. Now, how to control the output delay? Well, we can do that. Let's see how. Assume that your design is driving a flip-flop. We want to add an output delay on the output pins of 1.5 nanosecond relative to the system clock. So how we do it? We can do such by the command set output delay, and we mention the value 1.5, and we mention for which clock, that is CLK, and for all outputs. So this is how we can define the delay that is for input and as well as for the output. The purpose of this slide is just to touch base the basic concept of constraints and how the constraints transform an ideal case to a realistic case. I think that is being imprinted into your mind with this particular slide. So let's move on. Design constraint file. We have understood what is constraint and what purpose it is used for through small examples in last slide. In this slide, let me give you a compact introduction to the design constraint file. So here we go. Design constraint file, also known as SDC files, to impose initial timing conditions on the design. Adding constraint to the design is a process to make your design perform like a realistic situation, which I have been telling for last few minutes. Design constraint file have an .sdc file extension. Design constraint is a tickle based format to specify the design intent and the surrounding constraints for synthesis, clocking, timing, power, test, and area. This is a very important point. All the design constraint commands are nothing but tickle procedures. In the tickle series, I have already explained how the tickle works for VLSI. In case you have not watched that episode, I'll provide the link in the description. So guys, all these tickle commands are custom made tickle procedures, and they are very much intended application so that one particular command will do one thing. If you know tickle, you will be very easily write the tickle constraints based on the definitions that are provided in the manual. So guys, I think in upcoming examples, your mind will be very much clear that these are tickle commands and how we are using them. It can be generated during the synthesis stage using the tickle command. Write SDC, then the path, and then the name of the file .sdc. So this is a very widely used command, and this command is used at the synthesis stage to dump all the constraint into a file. We can write the constraint as well as we can dump the constraint. It all depends upon the tool which you are using. So don't think I'm making a global comment, but generally tools have this capability to read the SDC and write the SDC at synthesis stage, and it may vary from one vendor to another vendor. But just for your knowledge purpose, we are adding a fact that apart from writing it by hand, you can dump it also. Also, one can create the .sdc file manually in a text editor such as gvim, gedit, nano, notepad++. So I don't know which of text editor you are preferring. You can write down in the comment below which text editor you are very much comfortable with. And generally all these text editors nowadays have the highlighting capability. That means if you are using tickle, they will highlight the tickle proper names and keywords etc. in a different color and your normal values in a different color. So at least what I can say that you can write the commands manually and give it as an input to the tool, or you can dump it using the command just mentioned above. So I think we are done with this slide. Let's move on. Frequently used commands. Let me share a few design constraint commands that a designer very frequently have to use. You may consider this slide as your handbook. So here is our table. So let me bring my mouse. Set input delay. So this is a timing constraint and it sets the input delay of an input port relative to the clock signal. It's very straightforward in meaning, so I am not going any further explanation. Set output delay. This is also a timing constraint. It sets the output delay of an output port relative to a clock signal. So you have a clock in both the cases, and with these two commands you can set the input delay as well as the output delay. One thing I'd like to mention here, whichever tool you are using, just consult the manual for the rest of the arguments of this command. So that does make a sense, and that is very much needed, because when you are writing this file, those you have to write in a correct way so that whatever your thought process is to implement the constraint, that should be well reflected in the command. Now the third one, create clock. This is also a timing constraint. Creates a clock and defines its waveform in the current design. Set input transition. This is a system interface. Sets a fixed transition time on an input port. So this is basically a transition time, means that the slant, that means the rising or the falling. Set input transition, I think sets the load capacitance value on the output port. Here I think I have done some typo. I'll provide some more corrections in the description. So basically there is another command which is used for the load capacitance value for the output port. So I think the command would be something like that, set output load or something like that. These all commands are kind of frequently used command, and you can take them as for your handbook or something like that. You can write it somewhere in your notebook where all these commands and their arguments, so that you can easily use them whenever you are dealing with your actual design. Let me go to the next slide. Some more commands. So far we have discussed the most frequent commands. Now in this slide I will share some names of the commands which self-explanatory nomenclature. Some of these commands you may connect back with the ACA theories that I have covered in all of the previous episodes so far. So here we go for the list. Set clock, set clock delay, set current design, set false path, set input delay, set IO standard, set multi-cycle path, set output delay, set path delay, set range input delay, set range output delay. So all these names are kind of self-explanatory. You can easily understand and consult the manual whenever needed. The tickle commands are nothing but tickle procedures. So in different vendor tool, they can have a little bit difference in their names. Let me describe it to you. Generally the commands are set underscore then do something. If you look at the left side list, these are all like that. But in some other simulator, they can be like this. In some simulator, the commands may start with define, then underscore, then do some. So instead of set, it could be defined. It may vary from one simulator to another simulator, but the purpose remains the same. If you are encountering a different simulator, not only the name, the arguments may have been a bit different. So be careful and consult the manual every time. We are done with this particular slide. So let's move on. Recall the directed acyclic graph. So these are numbers, just don't panic. This slide is to give you a quick recall of the AT-RAT concept. Here goes our diagram, and you can see the numbers and everything has been well fitted inside it. Here goes our definition. Here goes our AT-RAT calculation, which we have discussed in episode 1. In case you have not seen or want to refresh your knowledge, use the chapter facility provided in the episode 1 description to quickly navigate to the respective slide. Link of episode 1 is provided in the description. So let's move on to the next slide. Arrival time, that is input delay. We just pictorially touch based the AT-RAT concept, which was discussed in detail in episode 1. Now let me show you how you can define the arrival time, that is input delay. Here goes our example. create a clock. First thing, create clock, then we specify the period 50, then name my clock, and then we use rectangular bracket as we use in Tickle, get ports my clock. So we get all the ports, and onto that we apply the period and everything. This is how we define create clock. Again, I am emphasizing from one simulator to another simulator, this particular command may be a bit different, so don't panic, always consult the manual. Defining input arrival time, that is 80. Set input delay 0 minimum, then rise for the ports get ports my clock. So here we set the rise time delay, clock is my clock, here the delay is 0. Set input delay 25, that is minimum, that is dash fall for falling edges. Get ports my clock, so get all the ports of this clock, and then clock name is my clock. Set input delay 0 max, that is rise, this is for rise transition. Get ports my clock, and clock name is my clock. Again, we have set input delay 25 max for fall, and get ports all the ports of my clock, and the clock name is my clock. So here you can say, let me bring my mouse, you can see that we have first defined the two minimums, and then we have defined the maximum of rise and fall, rise and fall. So all these rise and fall transition, we have defined the mean and max, the mean and max transitions. So this is how we create a realistic boundary that I have just spoke in the first slide. So we are done with this particular slide, so let's move on. Required arrival time, that is output delay. In this slide, I will exemplify command to define the required arrival time, that is output delay. Here goes our example. Define the output required arrival time, that is RAT. Set output delay 10, then we use the dash mean for minimum and rise, and then we use the get ports of out and clock name my clock. So here we are getting all the ports with out name and applying the delay of 10 for rise transition. Set output delay 10 minimum, and for fall transitions get ports, we get all the ports here through this command for out, and we set clock as my clock. Now we going for the max ones. Okay, yeah, set output delay 30 max, then for rise transition, and we use the get ports and clock is my clock. Set output delay 30 max, and then for fall transition and get ports for out and clock for my clock. So let me bring my mouse pointer again. If you compare, this remains static, this remains static, only the changes here it is static and here it is static, only changes is here and here. So we have couple of combinations just to declare the minimum and maximum of the delays for rise and fall type. So we have 4 total commands to define the realistic boundary for RAT, that is required arrival time. Here we are done with this particular slide, so let's move on. Rise, fall, slew design constraint. In this slide, we are going to exemplify the rise and fall slew constraints through commands. Here goes our example. Define the input transition time. Set input transition 10, then minimum, then rise, then get ports of input and clock is my clock. Set input transition 15 minimum for fall type transition, get ports for input and then clock my clock. Set input transition 20 max, rise, get ports for input and clock is my clock. And we define the set input transition 25 max, and for fall transition get all the ports input and then clock is my clock. So again, let me bring my mouse pointer. You can see the values are different, each value is different from one another, and here two are mean, these are two static, these are two static, but this is varying, here this is varying. So rise, fall, and here it is static, here it is static. So this is how we are defining the constraint for the input transition time. One more thing here I would like to add. Here we have defined with 1, but for your case you have to write multiple times for multiple cases. So it depends from one design to another design. So guys, we are done with this particular slide. So let's move on. Some more applications. Apart from the timing, we can do something with the design constraints commands. Let me show you how. Set realistic loads on each output pin. Set load 0.15 to all my outputs. This is how we can also add a load value. Set fan in and fan out for the input or output pins of your design. Set max fan out 1 to all of my outputs. So this rectangular bracket is a tickle concept. Now let us define the corresponding load. set fan out load 8 for all of my outputs. So this way we can use the design constraint. Apart from the timing things, we can define the load, fan out, fan in. You can consult the manual for all these types of other things that you can play around with the constraints. We are done with this slide, so let's move on. Thank you for watching up to this point. And don't forget to like, share and subscribe. If you have any kind of dislikes, put that in words in the comment section, and bye for today.